The story of water, from ancient oceans to glass. The first drop. Close your eyes for a moment and imagine a single drop of water suspended in time and space. Not just any drop, but one that has witnessed the birth of stars, the formation of our blue planet, and the endless dance between liquid and solid that would one day create something as miraculous as glass. This drop has been many things. It has been vapor in the breath of ancient volcanoes. It has been ice at the poles of distant worlds. It has been the ocean that cradled the first spark of life, and the rain that nourished the first forests. And today, in ways our ancestors could never have imagined, it has become part of the very glass through which we see the world. Tonight, we journey together through time, not just through years or decades, but through billions of years, to discover how water, that most essential of elements, became the silent partner in one of humanity's most transformative inventions, glass. This is a story that begins with the cosmos itself and ends in the gentle clink of a drinking glass, the soft glow of a window at sunset, or the smooth surface of your phone screen. It's a story about transformation, about patience, about the way the simplest things can become the most extraordinary, giving enough time, enough pressure, and enough human curiosity. So settle in, let your breathing slow, and prepare to be amazed by a tale that is both ancient and immediate, both scientific and magical. Because tonight, we're going to discover how water didn't just help create glass, it became glass in ways that will change how you see every transparent thing around you. In the beginning was water. $4.5 billion years ago, our planet was nothing like the world you know today. Picture, if you can, a sphere of molten rock tumbling through the darkness of space, its surface a churning sea of lava and fire. There were no continents, no mountains, no life, and most importantly for our story, no water. But water was coming. In the cold reaches of the outer solar system, comets, those ancient wanderers made of ice and dust, were beginning their long journey toward the sun. Each comet was like a frozen time capsule, carrying within its icy heart the very substance that would make our story possible. As these celestial messengers crashed into our young planet, they brought with them the gift that would change everything: H2O. 2 atoms of hydrogen, 1 of oxygen, bound together in a dance so simple and yet so profound that it would become the foundation of all life. Imagine the first moment when water touched our planet's surface and didn't immediately boil away into steam. The Earth had been cooling, slowly, patiently, for millions of years, and on that day, a day lost to time but remembered in every drop of water that exists today, the first ocean was born. But these weren't the blue, familiar oceans we know today. Picture instead vast, shallow seas of scalding water, rich with minerals and gases, under skies that glowed with volcanic light. The water was different then, more acidic, more reactive, more hungry for chemical transformation. It was water with a mission, though it didn't know it yet. In these ancient seas, something remarkable was happening. The water wasn't just sitting there, passive and still. It was working, dissolving rocks, carrying minerals, creating the first solutions that would later become crucial to our story. Every molecule of water was becoming a tiny laboratory, a place where elements could meet, and dance and combine in new ways. And in the depths of these ancient oceans, in places where underwater volcanoes met the sea, something almost magical was occurring. The intense heat of volcanic activity was creating natural glass, obsidian, as lava cooled rapidly in the water. It was crude, rough, nothing like the refined glass we know today, but it was the first chapter in the story of how heat, water, and minerals could combine to create something transparent, something that could show us the world in a new way. The water was learning, in its patient, geological way, how to be a partner in creation.
The Roman Revolution. Now let us journey westward and forward in time to the height of the Roman Empire around the 1st century CE. The Mediterranean world is connected by roads and trade routes, and knowledge flows between cultures like water finding its level. In a glass-making workshop on the island of Murano, which would later become famous for its glass, a Roman craftsman named Marcus Flavius is about to make a discovery that will change the world forever. He doesn't know it yet. The best discoveries are often made by people who are simply trying to solve a practical problem. Marcus has been struggling with the same challenge that plagued Egyptian glassmakers. His glass is cloudy and imperfect. But Marcus has something the Egyptians didn't have: access to a new technique that came from Syrian craftsmen who learned it from Phoenician traders who discovered it by accident when trying to purify their raw materials. The technique is called skimming, and it involves using water in a completely new way during the glassmaking process. Instead of simply heating the raw materials until they melt, Marcus has learned to add water to the molten glass mixture. Not liquid water, which would cause dangerous explosions, but water vapor, carefully introduced into the furnace at just the right moment. Here's where the magic happens. When water vapor meets molten glass at extremely high temperatures, it doesn't just create steam. It participates in complex chemical reactions that help remove iron impurities, the compounds that give glass its greenish or brownish tint. The water molecules break apart into hydrogen and oxygen atoms, and these atoms grab onto the iron compounds and carry them away as gas. It's as if the water is reaching into the molten glass and plucking out the impurities one by one, like a gardener removing weeds from a flower bed. Marcus doesn't understand the chemistry, but he sees the result. For the first time in human history, he's creating glass that is truly clear, not just translucent, not just pale, but genuinely transparent, glass you can see through as clearly as looking through air itself. The implications are staggering. This clear glass will become window glass, transforming architecture and the way humans live indoors. It will become mirrors, changing how people see themselves. It will become lenses, revolutionizing science and our understanding of the universe. And it will become vessels for drinking and storage that are so clear you can see exactly what's inside them. But perhaps most poetically, this clear glass represents something profound about water itself. Water, which is naturally transparent, has taught human beings how to make other materials transparent. It's as if water has shared one of its most essential qualities with the mineral world. In Marcus's workshop, as he lifts a piece of perfectly clear glass to the light and sees the world beyond it undistorted for the first time, he's witnessing the moment when water's ancient patience finally paid off. All those millions of years of wearing down mountains grain by grain, all that time spent as ice and vapor and rain, all those chemical dances in primordial seas, it was all preparation for this moment when water could finally teach humans one of its greatest secrets.
The ancient alchemists. Let us travel forward in time, past the formation of continents and the rise of the first life, past ice ages and the slow dance of evolution, to arrive in the ancient world, a time when humans first looked at water and wondered about its secrets. It's a warm evening in ancient Egypt, around 3,500 years ago.
The Nile River flows peacefully past mud brick homes, and in a small workshop near Memphis, a craftsman named Chaim Wasset is working by the light of an oil lamp. His hands, stained with the colors of his trade, are carefully shaping small beads of glass, some of the first deliberately created glass objects in human history. But Chaim Wasset doesn't fully understand what he's creating. He knows that when he heats certain sands with plant ash and a mysterious white powder we now call natron, a sodium carbonate that forms naturally where ancient lakes have dried up, something magical happens. The mixture melts and flows like honey, and when it cools, it becomes hard and clear, like captured water. What Chaim Wasset doesn't realize is that he's participating in one of the most beautiful partnerships in the history of technology. The natron he uses comes from dried lake beds, places where water once stood, slowly evaporating under the Egyptian sun, leaving behind concentrated minerals. The very absence of water has created one of the key ingredients he needs to make glass. And the sand itself? Each grain is a tiny library of geological history, formed over millions of years as water weathered mountains and carried their remains to ancient seabeds. The silica in that sand, the main ingredient in glass, was once part of living things, microscopic organisms called diatoms that lived in ancient oceans, their shells made of the same material that would one day become windows and mirrors. In Chaim Wasset's furnace, water plays multiple roles in the glassmaking process, though he doesn't understand the chemistry. When the raw materials heat up, water that's trapped in the sand and ash escapes as steam, helping to purify the mixture. The water vapor carries away impurities, leaving behind pure silica. It's as if the water is cleaning the other ingredients, preparing them for their transformation. As Chaim Wasset works, rolling the hot glass around the end of a bronze rod, he's unknowingly participating in a dance between the four classical elements: earth, the sand; fire, the furnace; air, the space the glass fills; and water, present in the steam, in the chemical process, and in the very structure of the glass itself. But Chaim Wasset's glass is cloudy and imperfect. It's beautiful in its own way, a milky white or pale blue, decorated with swirls of color that catch the light like trapped rainbows. These early glasses were precious, rare, worth more than gold. They were used for jewelry, small vessels, and ceremonial objects. The idea that glass could be perfectly clear, clear enough to see through, was still centuries away. The secret that was missing, though neither Chaim Wasset nor any of his contemporaries could have known it, was understanding water's role not just in making glass, but in making it clear. The medieval miracle. Time flows forward like a river, carrying us to medieval Europe, where glass and water are about to forge an even deeper partnership. It's the year 1291, and we find ourselves in Venice, in the workshops of Murano, where glassmakers have elevated their craft to an art form that borders on alchemy. Brother Giovanni, a Benedictine monk who has devoted his life to both prayer and the making of glass, stands before a furnace that burns day and night. The monks have discovered something remarkable, that the quality of water used in glassmaking affects not just the clarity of the final product, but its very strength and beauty. In his careful, methodical way, the same way he approaches his prayers, Brother Giovanni has been experimenting with different sources of water. Water from mountain springs produces glass with fewer bubbles. Water that has been blessed and purified through filtering produces glass that seems to sing when struck gently. And rainwater, collecting during thunderstorms and stored in consecrated vessels, produces glass with an almost supernatural clarity. What Brother Giovanni is discovering, without knowing the scientific principles behind it,
is that pure water creates better glass not just because it's free from impurities, but because of its molecular structure. Water molecules, with their unique bent shape and polar properties, interact with the silica in specific ways during the heating and cooling process. The purer the water, the more predictable these interactions become. But the monks have made another discovery, one that speaks to an even deeper connection between water and glass. They've learned that the way glass cools, a process called annealing, can be controlled by the careful application of water vapor. By introducing steam into the cooling process at precisely the right moments, they can control the internal stresses in the glass, making it stronger and less likely to crack. It's a process that requires not just technical skill, but something approaching meditation. The monk must feel the temperature of the glass, sense when it's ready for the next stage of cooling, know instinctively how much steam to introduce and when. It's a dance between human intuition and the fundamental properties of matter itself. In Brother Giovanni's workshop, this process takes on an almost spiritual dimension. As he works with the glass, he sees parallels with the transformation of the human soul. Just as raw sand and ash must be heated to extreme temperatures to achieve purity and clarity, so too must the human spirit endure trials to achieve clarity and strength. The water, in this metaphor, becomes a symbol of divine grace, something that comes from above, pure and life-giving, to help facilitate the transformation. The steam that rises from the cooling glass reminds Brother Giovanni of incense rising toward heaven, carrying prayers and intentions into the realm of the sacred. And indeed, much of the glass created in medieval monasteries was destined for sacred purposes. Stained glass windows that would transform light itself into something divine, chalices that would hold the wine of communion, reliquaries that would preserve sacred objects behind walls of perfect transparency. In these monastery workshops, the ancient partnership between water and glass was being refined into something that was both technically sophisticated and spiritually meaningful. The monks understood, perhaps better than anyone before or since, that the making of glass was not just a craft, but a form of prayer, a way of participating in the ongoing creation of the world.
The Renaissance Revelation. As the medieval world gives way to the Renaissance, our story of water and glass takes on new dimensions of wonder and discovery. It's the year 1608, and in a small workshop in Middelburg, Netherlands, a spectacle maker named Hans Lippershey is about to change humanity's relationship with the universe itself. Lippershey has been working with lenses, carefully shaped pieces of glass that can bend light in precise ways. But today, as he holds two lenses at just the right distance from each other and peers through them at the church tower across the square, something extraordinary happens. The tower, which should appear tiny from this distance, suddenly looms large and clear, as if he could reach out and touch its weathered stones. He has just invented the telescope. What Lippershey doesn't realize is that the lenses he's using owe their clarity and precision to centuries of water's patient work. The glass was made from sand that water had sorted and purified over millennia. The optical quality of his lenses depends on the absence of internal stresses that were controlled during manufacturing by the careful application of water vapor during the cooling process. But there's an even deeper connection at play. The way these lenses bend light follows the same principles that govern how light bends when it passes from air into water. When you look down into a clear pool and see a fish that appears closer to the surface than it really is, you're witnessing the same phenomenon that makes Lippershey's telescope work. Water, in its transparent simplicity, had been humanity's first optical instrument. Every time our ancestors looked into a still pond and saw their reflection, or noticed how objects appeared bent when partially submerged, they were learning about the behavior of light, lessons that would eventually enable them to craft glass into instruments that could reveal the hidden structures of reality itself. Within a year of Lippershey's discovery, Galileo Galilei has heard about this invention and created his own, more powerful version. On a clear evening in 1609, Galileo points his telescope toward the moon and sees something that changes everything. The lunar surface is not smooth and perfect, as philosophers had believed for millennia, but rough and mountainous, marked by craters and valleys. The moon, it turns out, has geology, landscapes shaped by the same forces that work on Earth, including the ancient action of water. Though Galileo doesn't know it yet, many of the features he's seeing were created billions of years ago, when the moon still had water on its surface, water that carved valleys and deposited sediments before evaporating into space. As Galileo continues his observations, discovering the moons of Jupiter and the phases of Venus, he's using an instrument that represents the ultimate partnership between human ingenuity and the natural properties of water and glass. The lenses are made from materials that water helped create and purify, shaped by techniques that water helped refine, and used to observe a universe where water has played a crucial role in shaping planets and moons. In Renaissance workshops across Europe, glassmakers are pushing their craft to new levels of sophistication. They're creating not just telescopes, but microscopes that reveal the hidden world of tiny creatures swimming in drops of pond water. They're making barometers and thermometers that use water and other liquids to measure the invisible forces of air pressure and temperature. Each of these instruments represents a conversation between human curiosity and the fundamental properties of matter. And water, in its various forms and roles, is present in every part of that conversation, as raw material, as tool, as subject of study, and as teacher of the optical principles that make precise observation possible.
The Industrial Awakening. The gentle rhythm of handicraft gives way to the thunderous pulse of machinery as we enter the Industrial Revolution. It's 1827. And in the bustling city of Birmingham, England, a glass manufacturer named Chance Brothers is about to revolutionize the relationship between water and glass in ways that will transform human civilization itself. Robert Lucas Chance stands in his factory, watching workers feed raw materials into furnaces that burn hotter and more consistently than any medieval monk could have imagined. Steam engines, powered by water heated into vapor, drive the machinery that mixes the raw glass ingredients with unprecedented precision. Water-powered bellows force air into the furnaces, creating temperatures hot enough to melt glass more completely than ever before. But the real revolution isn't just in how the glass is made, it's in how water is being used to shape it. Chance has pioneered a new technique called cylinder glass manufacturing, where molten glass is blown into large cylindrical shapes and then cooled with carefully controlled applications of water and steam. The cylinders are then cut and flattened to create large sheets of window glass. For the first time in history, ordinary people can afford windows large enough and clear enough to truly connect their indoor spaces with the world outside. The impact on human psychology and culture is profound. Homes become brighter, workplaces more pleasant, and the boundary between inside and outside begins to blur in ways that would have been unimaginable to our ancestors. But water's role in this transformation goes deeper than just manufacturing. The very buildings that house these new industrial processes are being designed around the availability of large, clear windows. Factory owners discover that workers are more productive when they can see natural light, and architects begin designing structures that maximize the use of glass and the interplay between interior and exterior spaces. In Chance's factory, water is everywhere, serving multiple crucial functions. Steam engines convert water to vapor to power the machinery. Water cools the glass at precisely controlled rates to prevent cracking. Water carries away waste heat from the furnaces, and water in the form of carefully maintained humidity keeps the working environment suitable for the delicate process of glass formation. The workers in the factory develop an almost intuitive understanding of water's moods and behaviors. They learn to read the steam rising from cooling glass like others might read the weather. They know the exact sound that water makes when it hits glass at the perfect temperature for cooling. They understand that the quality of their product depends not just on fire and sand, but on water's willing partnership in the transformation process. Meanwhile, across the Atlantic, American glassmakers are pushing these techniques even further. In Pennsylvania and West Virginia, where high-quality sand and abundant water sources create ideal conditions for glass manufacturing, entire towns are being built around the glass industry. The relationship between geography, water resources, and glass production becomes so intimate that the location of rivers and springs directly determines where cities will grow and prosper. These American glassmakers make another crucial discovery. Different sources of water produce subtly different results in the glass. Water from certain rivers filtered through specific types of rock and soil contains trace minerals that actually improve the clarity and workability of glass. Other water sources, while perfectly good for drinking, produce glass with slight tints or structural weaknesses. This leads to the development of water treatment specifically for industrial glass making, one of the first times in human history that water has been deliberately modified, not for human consumption, but to improve a manufacturing process. The technology developed for purifying water for glassmaking will eventually contribute to improved public water supplies and better understanding of water chemistry in general. The Crystal Palace Dream. In the heart of London, in the year 1851, something unprecedented is taking shape in Hyde Park. Joseph Paxton, a gardener turned architect, is overseeing the construction of a building unlike any the world has ever seen, a vast cathedral made almost entirely of iron and glass. They're calling it the Crystal Palace, and it represents the ultimate marriage of human ambition with the ancient partnership between water and glass. The Crystal Palace uses over 293,000 panes of glass, each one representing countless centuries of geological preparation, human innovation, and water's patient work. But the building itself is designed around principles that Paxton learned from studying water plants, particularly the giant water lily Victoria regia, whose leaves can support the weight of a small child through a network of radial and circular ribs. Paxton realized that glass, like the surface of a lily pad, is strongest when supported by a framework that distributes stress evenly. His Crystal Palace uses iron ribs arranged in patterns inspired by plant structures, creating a building that is both incredibly strong and almost impossibly light and airy. But there's a deeper connection between the Crystal Palace and water that goes beyond structural inspiration. The building is designed to create its own weather inside. The vast glass surfaces allow sunlight to enter, creating a greenhouse effect that keeps the interior warm even in the English winter. But the same glass also allows water vapor from the hundreds of plants displayed inside to rise and condense on the inner surfaces of the roof, creating a gentle, constant drizzle that waters the exhibits below. The Crystal Palace becomes, in effect, a giant terrarium, a closed ecosystem where water cycles naturally from soil to air to condensation and back to soil again. Visitors walk through this space feeling as if they're inside a jewel or a soap bubble, surrounded by light and air and the gentle sound of water finding its way back to earth. The success of the Crystal Palace inspires architects around the world to experiment with glass in new ways. In Paris, Henri Labrouste designs the Bibliothèque Sainte-Geneviève with vast reading rooms lit by skylights that seem to dissolve the boundary between interior and exterior space. In New York, James Bogardus creates cast-iron buildings with huge windows that bring natural light deep into commercial spaces. Each of these buildings represents a new understanding of how glass can be used not just as a barrier between inside and outside, but as a medium for connecting human spaces with the natural world. The glass becomes a membrane that allows light and visual connection while providing protection from weather and climate. But perhaps most importantly, these great glass buildings change how people think about transparency itself. In medieval times, glass was precious and rare, used sparingly in small windows that provided glimpses of the outside world. In these new buildings, transparency becomes abundant, generous, transformative. People begin to speak of transparency in new ways, not just as a physical property of materials, but as a social and political ideal. The Crystal Palace, with its complete openness and visibility, becomes a symbol of democratic values, international cooperation, and the sharing of knowledge and culture across national boundaries. The building materials themselves tell the story of global connection. Sand from different continents, soda ash from various sources, and water from the Thames, all combine to create something that belongs not to any one nation, but to humanity as a whole. When the Great Exhibition ends and the Crystal Palace is moved to South London, it continues to serve as a symbol of what's possible when human creativity partners with the fundamental properties of matter. For nearly a century, until it's destroyed by fire in 1936, the Crystal Palace stands as a testament to the transformative power of transparency, light, and the ancient alliance between water and glass.
The scientific revolution. As the 19th century progresses, the relationship between water and glass enters a new phase of sophistication. In laboratories across Europe and America, scientists are beginning to understand the molecular basis of glass formation, and water's role in that process is revealing itself to be even more complex and beautiful than anyone had imagined. In 1884, at the University of Jena in Germany, a young chemist named Otto Schott is conducting experiments that will revolutionize our understanding of glass chemistry. Working with the renowned physicist Ernst Abbe, Schott is systematically studying how different chemical compositions affect the properties of glass. His laboratory is filled with precisely controlled furnaces, carefully calibrated instruments, and most importantly for our story, apparatus for controlling the exact amount of water vapor present during glass formation. What Schott discovers changes everything. He finds that water doesn't just help purify glass during manufacturing, it actually becomes part of the glass structure itself. When glass is formed in the presence of water vapor, tiny amounts of hydroxyl groups, OH-, become incorporated into the silica network. These hydroxyl groups, barely detectable but chemically significant, affect everything from the glass's optical properties to its chemical resistance. This discovery leads to the development of different types of glass optimized for specific purposes. Borosilicate glass, which incorporates boron oxide along with silica, can withstand extreme temperature changes because of how water molecules interact with its structure during formation. Crown glass, used for precision optics, requires water vapor to be controlled to within incredibly tight tolerances to achieve the required optical clarity. Meanwhile, in Thomas Edison's laboratory in Menlo Park, New Jersey, the partnership between water and glass is enabling another revolution, the practical electric light bulb. Edison's team discovers that creating a perfect vacuum inside glass bulbs requires understanding how water vapor behaves at different temperatures and pressures. Even tiny amounts of water vapor left inside the bulb will cause the tungsten filament to degrade rapidly. The solution involves a process called gettering, where materials that readily absorb water are placed inside the bulb during manufacturing. As the bulb is heated, these materials capture any remaining water vapor, creating the pristine vacuum necessary for long bulb life. It's a process that requires understanding water's behavior at the molecular level, knowledge that would have seemed like magic to the ancient glassmakers of Egypt or Rome.
But perhaps the most profound scientific advance of this era is the development of analytical instruments that depend on ultra-pure glass. In 1859, Gustav Kirchhoff and Robert Bunsen developed spectroscopy, a technique for identifying chemical elements by the specific colors of light they emit when heated. Their spectroscopes require optical glass of unprecedented purity and precision. The glass for these instruments must be so free from impurities that the manufacturing process becomes almost ceremonial in its precision. The sand is washed repeatedly with distilled water. The water used for cooling is purified to remove even trace minerals. The glass is formed in furnaces where the atmosphere is carefully controlled to prevent any contamination. These precision instruments make possible the discovery of new chemical elements, the analysis of distant stars, and eventually the development of quantum mechanics. Each discovery builds on the foundation of perfectly transparent glass that achieves its clarity through water's ancient ability to purify and transform. In university laboratories, students learn to clean glassware with a precision that would have amazed medieval alchemists. They use distilled water, deionized water, and water purified through multiple processes to ensure that their experiments revealed the true behavior of matter, rather than the interference of impurities. The ritual of cleaning glassware becomes a meditation on purity, precision, and the importance of understanding materials at the molecular level. The liquid crystal revolution. In 1968, in a small laboratory at RCA in Princeton, New Jersey, engineer George Heilmeyer is working with a substance that seems to challenge everything we know about the relationship between liquid and solid states. He's studying liquid crystals, materials that flow like liquids but have molecular structures as ordered as crystals. And he's about to discover how these strange materials can partner with glass to create entirely new ways of seeing and displaying information. The liquid crystal display, or LCD, represents perhaps the most intimate partnership between water-derived materials and glass since the invention of clear window glass itself. The liquid crystals are organic compounds that often contain water molecules as part of their structure, while the substrates that contain them are made of glass so flat and smooth that their surfaces are measured in fractions of wavelengths of light. What makes this technology so remarkable is how it exploits the fundamental properties of both materials. The glass provides a perfectly stable, transparent substrate that doesn't interact chemically with the liquid crystals. Meanwhile, the liquid crystals can change their optical properties, their ability to rotate polarized light when subjected to tiny electrical currents. The manufacturing process for LCD displays requires control of water at levels that surpass even semiconductor fabrication. The liquid crystal materials must be absolutely free from water contamination, as even a few molecules of H2O can disrupt the delicate molecular alignment that makes the displays work. The glass substrates must be cleaned with water so pure that it leaves no residue whatsoever. Water that is literally more pure than natural rainwater by factors of millions. But there's a deeper poetry to how LCDs work. Light entering the display passes through polarizing filters, then through the liquid crystal layer, then through color filters, and finally through the glass substrate to reach your eyes. At each stage, the light is being modified, controlled, and directed by materials that trace their origins back to water's ancient work of geological transformation. The polarizing filters are made from polymers that are stretched and aligned in processes that use water as a solvent and processing aid. The color filters are created using pigments that are washed and purified to incredible levels of purity. Even the adhesives that hold the various layers together are formulated using water-based chemistry principles. When you look at a modern LCD screen, whether it's your phone, your computer monitor, or a massive display in Times Square, you're looking through a stack of materials whose creation required the coordination of water and glass technologies developed over centuries. The light reaching your eyes has been shaped by materials that exist at the intersection of ancient glassmaking knowledge and
cutting-edge molecular engineering. The evolution of display technology reveals water's continuing role in unexpected ways. OLED displays, which create light directly from organic compounds rather than filtering back light through liquid crystals, require glass substrates that are not only incredibly pure, but also perfectly moisture-proof. Water vapor is one of the primary enemies of OLED materials, causing them to degrade rapidly if not completely sealed away from atmospheric moisture. This has led to the development of barrier coatings, essentially ultra-thin layers of glass applied to plastic or glass substrates that can prevent water molecules from penetrating flexible displays. These coatings are so effective that they can reduce water permeability to levels lower than traditional glass sheets hundreds of times thicker.
The digital revolution. In the clean rooms of Silicon Valley in the early 1960s, the ancient partnership between water and glass is about to enable a revolution that will transform human civilization as profoundly as the invention of writing or the printing press. At Fairchild Semiconductor, engineer Robert Noyce is working with incredibly pure silicon. Silicon derived from the same sand that ancient glassmakers used, but purified to levels that would have been inconceivable just decades earlier. The process of creating this ultra-pure silicon requires water of unprecedented purity. Every step of silicon purification involves washing with water that has been distilled, deionized, and filtered to remove impurities measured in parts per billion. The water used in semiconductor manufacturing is literally millions of times purer than drinking water, cleaner than anything that exists naturally on Earth. But the connection between this work and traditional glassmaking goes deeper than just pure materials. The techniques used to grow silicon crystals are directly descended from methods developed by glass researchers. The controlled cooling processes, the precise temperature management, the understanding of how crystal structure affects material properties, all of these trace their lineage back to centuries of glassmaking knowledge. The silicon wafers that Noyce and his colleagues produce are then coated with layers of silicon dioxide, essentially a form of glass just nanometers thick. These glass layers serve as insulators in the first integrated circuits, enabling the creation of transistors small enough to fit thousands on a single chip. The glass must be so uniform that variations in thickness are measured in individual atoms. As the semiconductor industry develops, the requirements for water purity become even more extreme. Modern semiconductor fabrication facilities, called fabs, use water systems that produce H2O so pure that it's actually a better electrical insulator than air. This ultra-pure water is used not just for cleaning, but as a raw material in the chemical processes that create the microscopic structures of computer chips. The glass-like materials used in modern electronics extend far beyond simple silicon dioxide. Engineers develop complex glass compositions containing dozens of different elements, each chosen for specific electrical or optical properties. Some of these glasses conduct electricity, others block it completely. Some are transparent to visible light, but opaque to infrared radiation. Others can switch between transparent and opaque states when subjected to electrical currents. But perhaps the most poetic connection between ancient glassmaking and modern technology lies in optical fibers, strands of ultra-pure glass thinner than human hair that carry information as pulses of light. The glass used in these fibers must be so free from impurities that light can travel through them for dozens of kilometers without significant loss. Creating such pure glass requires understanding water's role at the molecular level. Even tiny amounts of hydroxyl groups, OH-, in the glass can absorb specific wavelengths of infrared light, causing signal loss. Fiber optic glass must be manufactured in environments where water vapor is controlled to parts per billion,
using furnaces that operate in carefully controlled atmospheres of ultra-pure gases. The result is a material that surpasses even the clearest natural crystals in its optical properties. Light travels through optical fibers with less loss than it experiences traveling through air. These glass threads become the nervous system of the global internet, carrying conversations, images, and data across continents at the speed of light. In research laboratories around the world, scientists are pushing the boundaries of what glass can do even further. They're creating glasses that can store information at the quantum level, materials where individual photons can be trapped and manipulated. They're developing self-healing glasses that can repair microscopic cracks automatically, and smart glasses that can change their properties in response to external stimuli. The connection to water remains profound and intimate. Every breakthrough in glass technology requires deeper understanding of how water molecules interact with glass structures. Every advance in purity demands more sophisticated water treatment. Every new application reveals new ways that the ancient partnership between hydrogen, oxygen, and silicon continues to shape our technological future.
The modern synthesis. As we enter the 20th century, the ancient partnership between water and glass is about to be transformed by a revolutionary new understanding of atomic and molecular structure. In 1932, at the Corning Glass Works in upstate New York, a materials scientist named Eugene Sullivan is working on a problem that has puzzled glassmakers for centuries: how to create glass that is simultaneously stronger, clearer, and more chemically resistant than anything previously achieved. Sullivan's approach is fundamentally different from that of his predecessors. Instead of relying on intuition and tradition, he's using X-ray crystallography to study the actual atomic structure of glass as it forms. What he discovers is that water doesn't just interact with glass during manufacturing, it continues to interact with glass throughout its entire existence, in ways so subtle they had never been noticed before. Glass, it turns out, is not as stable as it appears. At the molecular level, it's constantly changing, with water molecules from the atmosphere slowly penetrating the surface and causing microscopic changes in structure. This process, called weathering, explains why ancient glass objects sometimes develop an iridescent patina, and why glass windows in old buildings sometimes become slightly wavy over time. Understanding this process allows Sullivan and his team to design glass compositions that are more resistant to water's slow but persistent effects. They develop new formulations where the silicon network is more tightly bonded, creating glass that can maintain its clarity and strength for centuries rather than decades. But Sullivan's most significant contribution comes from understanding how water behaves during the glass cooling process. Using high-speed photography and temperature sensors, he maps exactly how water vapor moves through cooling glass, creating or relieving internal stresses. This knowledge leads to the development of controlled annealing processes that can create glass objects with predetermined stress patterns, glass that is stronger in specific directions, or that will break in predictable ways for safety applications. Meanwhile, across the Atlantic, scientists at the Pilkington Glass Company in England are working on what will become one of the most important innovations in glass manufacturing history: the float glass process. Developed by Alistair Pilkington, no relation to the company's founders, this revolutionary technique creates perfectly flat glass by floating molten glass on a bath of liquid tin. But water plays a crucial role in this process too. The atmosphere above the tin bath must be carefully controlled to prevent oxidation, and this is achieved using a mixture of nitrogen and hydrogen gases. The hydrogen comes from water that has been split into its component atoms using electrical energy. As the glass floats on the tin, water vapor is used to control the cooling rate and ensure uniform thickness. The result is glass with optical quality so superior to previous manufacturing methods that it revolutionizes everything from architecture to automobile manufacturing. The perfectly flat surfaces and consistent thickness made possible by the float process enable the development of large curtain wall buildings where entire facades can be made of glass with minimal visible supporting structure. In the post-World War II era, the partnership between water and glass takes on a new urgency as scientists work to develop materials for the space age. Glass components for spacecraft must survive extreme temperature variations, intense radiation, and the complete absence of water vapor that characterizes the space environment. This leads to the development of ultra-low expansion glasses, where the thermal properties are controlled so precisely that the glass barely changes size even when subjected to temperature swings of hundreds of degrees. These glasses require manufacturing processes where every molecule of water vapor is accounted for, where humidity is controlled to fractions of a percent, and where the interaction between water and glass is understood at the quantum mechanical level.
The fiber optic web. Deep beneath the Atlantic Ocean, in the crushing darkness 2 miles below the surface, a cable no thicker than a garden hose carries conversations, emails, videos, and dreams between continents at the speed of light. This is a fiber optic cable, and at its heart are strands of glass so pure that if the ocean were made of this glass, you could see the bottom as clearly as looking through window glass just a few feet thick. The story of these underwater glass highways begins in 1966 when physicist Charles Cow at Standard Telecommunication Laboratories in England calculated that glass fibers could theoretically carry light signals over long distances with very little loss, if they could be made pure enough. At the time, the purest glass available lost so much light that signals could travel only a few meters before becoming too weak to detect. Cow's insight was that the problem wasn't fundamental to glass itself, but rather to the impurities within it. He predicted that if glass could be made pure enough, removing impurities to levels of less than 1 part per billion, then light signals could travel for kilometers without significant loss. The challenge was achieving this level of purity, and water played a crucial role in the solution. The manufacturing process, developed by Corning Glass Works in the early 1970s, begins with ultra-pure silicon trichloride gas, which is heated in the presence of water vapor and oxygen to create tiny particles of incredibly pure silica glass. But here's where the process becomes almost alchemical in its precision. The water used in this process must be isotopically pure. Natural water contains small amounts of heavy water, deuterium oxide, and even these trace amounts can cause optical losses in fiber optic glass. The water is purified not just chemically, but isotopically, removing even naturally occurring variations in atomic weight. The silica particles created by this process are deposited on the inside of a rotating glass tube, building up layer by layer to create what's called a preform. This preform is then heated and drawn into fiber optic strands thousands of times thinner than the original tube, but with the same optical properties maintained throughout their length. The drawing process itself requires water cooling systems that can remove heat at precisely controlled rates. Too fast, and the glass develops internal stresses that scatter light. Too slow, and the glass crystallizes, becoming opaque. The cooling water must be precisely temperature controlled and free from minerals that could cause uneven heat transfer. As these fibers are installed in undersea cables, they're protected by multiple layers of materials, but water remains both an enemy and, paradoxically, a protector. The cables must be absolutely waterproof to prevent the glass fibers from degrading, but they also rely on the ocean itself for protection from ship's anchors and other hazards. The global internet that these cables create represents the fulfillment of an ancient human dream: instantaneous communication across any distance. When you video call someone on another continent, your voice and image are converted to pulses of light that travel through glass threads at nearly 200,000 kilometers per second, bouncing off the walls of tubes so pure that they lose less than 3% of their light traveling from New York to London. But perhaps most remarkably, the manufacturing of these fibers requires returning to some of the oldest principles of glassmaking. The furnaces used to draw optical fiber operate at temperatures similar to those used by Roman glassmakers 2,000 years ago. The basic process, heating silica until it flows, then shaping it while controlling the cooling rate, would be recognizable to medieval monks, even though the precision required is measured in billionths rather than inches.
The smart glass revolution. In laboratories around the world today, researchers are creating materials that would seem like magic to ancient glassmakers, glasses that can think, respond, and adapt to their environment. These smart glasses represent the next chapter in the eternal partnership between water and glass, where nanotechnology meets millennia of accumulated knowledge about how materials can be shaped and controlled. At MIT's Materials Science Laboratory, Dr. Sarah Chen is working with electrochromic glass, material that can change from transparent to opaque at the flip of a switch. The glass contains layers of materials just nanometers thick, including metal oxides that can absorb or reflect light when tiny electrical currents are applied to them. The manufacturing of these smart materials requires understanding water's role at scales that would have been unimaginable even 50 years ago. The metal oxide layers are often deposited from solutions where every water molecule's position and behavior must be controlled. The substrates are cleaned using water purified through processes that remove not just chemical impurities, but also ensure that no unwanted molecular structures remain on the glass surface. But Dr. Chen's work goes beyond simple transparency control. She's developing glasses with embedded sensors that can detect humidity, temperature, and even the chemical composition of the air around them. These sensors are created using techniques that combine traditional glass chemistry with cutting-edge nanotechnology, creating materials that can literally feel their environment and respond accordingly. The most advanced smart glasses being developed today can switch between different optical states in milliseconds, can display information directly on their surface, and can even generate their own electrical power using ambient light. All of these functions depend on controlling the interaction between water molecules and glass substrates at the atomic level. In Japan, researchers at Tokyo University are working on self-healing glass, materials that can automatically repair small cracks and scratches. The healing mechanism involves microscopic capsules embedded in the glass structure that contain reactive chemicals, including water-based solutions that can polymerize to fill gaps in the material. When the glass is damaged, these capsules break and release their contents, which then react with moisture from the air to form new glass-like materials that restore the original optical and mechanical properties. It's as if the glass has learned to use water as a healing agent, the way living tissues use blood to repair injuries. But perhaps the most profound development in smart glass technology is the creation of materials that can store and process information. Researchers are developing glasses where data can be written using laser pulses and read using changes in optical properties that persist for thousands of years. These storage systems use the fundamental structure of glass itself as the medium for information storage, creating archives that could survive longer than human civilization. The process of writing information into glass involves creating microscopic changes in the glass structure using focused laser beams. These changes are so small that they don't affect the glass's transparency or strength, but they can be detected using specialized optical equipment. Water plays a crucial role in stabilizing these structures, with hydroxyl groups helping to prevent the stored information from degrading over time. The biological interface. In a research hospital in Boston, surgeon Dr. Maria Rodriguez is performing a procedure that would have seemed like science fiction just decades ago. She's implanting a glass-based neural interface directly into a patient's brain, a device that will allow the patient to control computer systems using thought alone. The biocompatible glass used in this device represents one of the most sophisticated applications of glass technology ever developed, and water is integral to making it work safely in the human body. The human body is approximately 60% water, and any material implanted in the body must be able to function in this aqueous environment without causing harmful reactions. The glass used in biomedical implants is specially formulated to be chemically stable in bodily fluids, which are essentially complex saltwater solutions with carefully controlled pH levels. But these biomedical glasses do more than simply resist corrosion. They're designed to interact with the body's chemistry in beneficial ways. Some bioactive glasses actually bond with bone tissue, using the water and minerals present in blood to create chemical connections that help integrate the implant with living tissue. Dr. Rodriguez's neural interface uses glass electrodes so thin that they can be inserted into individual brain cells without causing damage. These electrodes are made from glass that has been doped with conductive materials, creating a hybrid that combines glass's biocompatibility with the electrical properties needed to detect neural signals. The manufacturing process for these neural interfaces requires controlling water at the cellular level. The glass must be absolutely free from bacterial contamination, which means using water that has been sterilized not just chemically, but also biologically. The production facilities use water treatment systems that ensure every molecule of H2O has been purified to medical-grade standards. But the most remarkable aspect of these biomedical applications is how they're teaching us new things about the fundamental relationship between glass and water. Researchers have discovered that the surface properties of glass, how it interacts with water molecules at the molecular level, can influence how cells grow and behave when they come in contact with the material. By modifying the glass surface at the nanoscale, scientists can create materials that encourage certain types of cells to grow while discouraging others. Some glasses can be designed to slowly dissolve in bodily fluids, releasing beneficial ions like calcium and phosphorus that promote healing. Others can be made to resist protein buildup, preventing the formation of scar tissue around implants. At the University of California, researchers are developing smart contact lenses made from glass polymer composites that can monitor glucose levels in tears, potentially providing diabetic patients with continuous blood sugar monitoring without the need for painful finger pricks. These lenses use glass sensors so small they're invisible to the naked eye, embedded in materials that remain comfortable and safe for direct contact with the eye. The manufacturing of these contact lenses requires understanding how glass behaves when formed into structures just microns thick. The glass must maintain its optical clarity while being flexible enough to conform to the curved surface of the eye. Water is used throughout the manufacturing process to control the formation of these ultra-thin glass layers and to test their permeability and biocompatibility.
The quantum frontier.
Deep in the underground laboratories of CERN, the European Particle Physics Laboratory, physicist Dr. Elena Volkov is working with materials that exist at the very edge of human understanding. She's developing quantum sensors made from ultra-pure glass that can detect individual photons, single particles of light, and potentially revolutionize our ability to manipulate information at the quantum level. These quantum sensors represent the ultimate refinement of the ancient partnership between water and glass. The glass used in quantum applications must be so pure that it contains fewer than 1 impurity atom per billion glass atoms. Even more remarkably, the position of water molecules within the glass structure must be controlled with precision measured in fractions of nanometers. The reason for this extreme precision lies in the strange world of quantum mechanics, where particles can exist in multiple states simultaneously, and where the act of observation can change the behavior of the system being observed. In quantum sensors, individual photons are trapped in glass structures called optical cavities, where they can exist in superposition states, simultaneously present and absent until they're measured. Water molecules, with their asymmetric structure and polar properties, can disrupt these delicate quantum states if they're not precisely controlled. The glass must be manufactured in environments where not only is water vapor controlled to parts per billion, but where the isotopic composition of any remaining water is carefully specified. Dr. Volkov's team has discovered that certain configurations of hydroxyl groups, OH- in glass, can actually enhance quantum effects rather than disrupting them. By precisely controlling where these water-derived groups are located within the glass structure, they can create materials that trap and manipulate quantum states more effectively than any purely synthetic material. But perhaps the most extraordinary application of quantum glass technology is in quantum computing, where information is processed using quantum bits, or qubits, that can exist in superposition states. Some approaches to quantum computing use photons trapped in glass structures as qubits, requiring materials where the interaction between light and glass can be controlled at the single photon level. The manufacturing of quantum glass components requires returning to some of the most fundamental principles of glassmaking, but applying them with precision that surpasses anything previously attempted. The furnaces used to create quantum glass operate at temperatures controlled to fractions of degrees, using water cooling systems that can maintain thermal stability measured in thousandths of degrees Celsius. The annealing process, the controlled cooling that determines the final structure of the glass, must be so precisely controlled that temperature changes are measured in degrees per hour rather than the degrees per minute used in conventional glass manufacturing. Water plays a crucial role in this process, both as a coolant and as a source of the hydroxyl groups that give the final glass its quantum properties.
The environmental awakening. As the 21st century progresses, the ancient partnership between water and glass is being called upon to help solve some of humanity's greatest challenges. In laboratories and factories around the world, researchers are developing glass-based technologies that could help address climate change, water scarcity, and environmental degradation, returning to glass's roots as a material created through the patient work of natural processes. At the National Renewable Energy Laboratory in Colorado, materials scientist Dr. James Kim is working on next-generation solar panels that use specially designed glass to capture and convert sunlight more efficiently than ever before. These panels use glass substrates with precisely controlled surface textures that trap light, increasing the amount of energy that can be harvested from each photon of sunlight. The glass used in these solar panels must withstand decades of exposure to weather, temperature cycling, and ultraviolet radiation while maintaining its optical properties. Water plays a crucial role in both manufacturing and testing these materials. During production, water vapor is used to create the microscopic surface textures that give the glass its light-trapping properties. In testing, the panels are subjected to accelerated weathering tests that simulate years of rain, humidity, and temperature changes. But Dr. Kim's work goes beyond simply improving existing solar technology. He's developing smart solar glass that can adjust its properties based on weather conditions. On cloudy days, the glass becomes more transparent to capture diffuse light. On bright days, it can reflect excess light to prevent overheating. The switching mechanism relies on water-sensitive materials embedded in the glass structure that respond to humidity changes in the surrounding air. Meanwhile, in Singapore, where fresh water is a precious resource, engineers are developing atmospheric water generators that use glass-based condensation systems to extract drinking water directly from air. These systems use specially textured glass surfaces that encourage water vapor to condense even at relatively low humidity levels. The glass surfaces in these water harvesting glasses are inspired by desert plants and animals that have evolved to capture water from fog and dew. The manufacturing process creates microscopic patterns on the glass surface, some areas that attract water molecules and others that repel them, creating channels that guide condensed water toward collection points. The production of these water harvesting glasses requires understanding surface chemistry at the molecular level. Different areas of the glass surface are treated with water-loving or hydrophilic and water-repelling or hydrophobic coatings applied using techniques that ensure the patterns remain stable for years of operation. The glass itself must be chemically resistant to the various compounds that might be present in atmospheric water, from salt spray near oceans to industrial pollutants in urban areas. In the Netherlands, where rising sea levels threaten coastal communities, engineers are developing new types of glass that can help protect buildings from flooding. These flood-resistant glasses use laminated structures with water-activated sealants that expand when exposed to moisture, creating increasingly watertight seals as flood conditions worsen. But perhaps the most promising environmental application of glass technology is in carbon capture and storage. Researchers are developing glass-based materials that can selectively absorb carbon dioxide from the atmosphere, potentially helping to reverse the greenhouse gas accumulations that drive climate change. These carbon capture glasses use surface modifications that create molecular-sized pockets specifically shaped to trap CO2 molecules. Water plays a dual role in these systems. It helps create the surface structures during manufacturing, and it can be used to release the captured carbon dioxide for storage or utilization in controlled environments.
The healing arts. In a quiet laboratory at Johns Hopkins University, biomedical engineer Dr. Rachel Pertel is developing glass-based materials that could revolutionize how we treat injuries and diseases. Her work represents a return to glass's earliest role in human culture as a tool for healing and restoration, but applied with 21st century understanding of how materials interact with living systems. Dr. Pertel's team is creating bioactive glasses that can actually stimulate the growth of new bone tissue. When implanted in the body, these glasses slowly dissolve in the aqueous environment of bodily fluids, releasing ions like calcium, phosphorus, and silicon that encourage bone cells to multiply and form new tissue. The glass literally disappears as it's replaced by living bone, leaving behind no foreign material in the patient's body. The chemistry behind these bioactive glasses depends on carefully controlling how water interacts with the glass structure. As bodily fluids contact the glass surface, water molecules begin breaking the bonds between silicon and oxygen atoms, gradually dissolving the glass network. But this dissolution must happen at just the right rate, fast enough to release beneficial ions, but slowly enough to maintain the glass's structural integrity until new tissue can form. The manufacturing process for bioactive glasses requires understanding water's role in ways that would have amazed ancient healers who used natural glasses like obsidian for surgical tools. The raw materials must be melted and cooled in precisely controlled atmospheres, where water vapor content affects not only the glass's initial properties, but also how it will behave when implanted in the body. The artist's vision. In a converted warehouse in Brooklyn, glass artist Maya Chen is working on a sculpture that will challenge everything people think they know about the relationship between art and technology. Her piece, titled Memory of Water, uses smart glass technologies developed for high-tech applications to create artworks that respond to viewers' presence, changing color and transparency based on the humidity of their breath, the warmth of their bodies, and even their emotional state as measured by subtle changes in bioelectrical fields. Maya's work represents a return to glass's role as a medium for beauty and spiritual expression, but informed by centuries of scientific understanding about how glass and water interact at the molecular level. Her sculptures incorporate electrochromic glasses that can shift between different colors, thermochromic materials that respond to temperature, and even glasses doped with phosphorescent compounds that can store and release light energy over time. The creation of these artistic pieces requires the same level of precision as the most advanced technological applications. Maya works with glass manufacturers who can create custom formulations for her specific artistic vision, controlling not just the optical properties of the glass, but also how it responds to environmental changes. One of her most acclaimed works is a glass installation that recreates the water cycle within the gallery space. Moisture from visitors' breath condenses on carefully cooled glass surfaces, forming droplets that roll down textured channels to collection points. The collected water is then pumped to the top of the installation, where it evaporates from heated glass plates, beginning the cycle anew. The installation uses glasses with different wetting properties. Some surfaces attract water, while others repel it to control exactly how the water moves through the system. Visitors can see their own breath literally becoming part of the artwork, their exhalation joining the eternal cycle of evaporation and condensation that has shaped our planet for billions of years. Maya's artistic process involves understanding glass at the same molecular level as the scientists and engineers who develop high-tech applications, but applying that knowledge to create experiences that speak to human emotions and imagination. She studies how different glass compositions affect the way light scatters through water droplets, how surface textures influence the formation of frost patterns, and how optical coatings can create interference effects that shift with viewing angle. But Maya's work also explores the historical and cultural dimensions of glass and water. In one series of pieces, she recreates glass formulations used by ancient civilizations, showing how the optical properties of Roman glass differ from medieval glass or modern formulations. Visitors can see how the same sunlight looks different when filtered through glasses made using techniques separated by centuries or millennia. Her most ambitious project is a large-scale installation that traces the journey of water through geological time using glasses that incorporate actual materials from different geological eras. Ancient sand from the Sahara Desert, volcanic glass from Iceland, and sediments from deep ocean cores are incorporated into glass panels that tell the story of water's role in shaping our planet. The installation uses advanced lighting systems to show how the same materials appear different under various wavelengths of light, revealing features that are invisible to the naked eye. Visitors can see trace minerals that indicate ancient ocean chemistry, microscopic fossils embedded in the glass, and structural patterns that reveal how the materials were formed under different temperature and pressure conditions. Through Maya's artistic vision, the scientific story of water and glass becomes a sensory experience that engages not just the intellect, but also the emotions and imagination. Her work reminds us that the ancient partnership between these materials is not just a technological story, but also a deeply human one, touching our need for beauty, meaning, and connection with the natural world.
The future unfolding. As we stand at the threshold of new scientific and technological frontiers, the partnership between water and glass continues to evolve in directions that would have seemed impossible to previous generations. In research laboratories around the world, scientists are developing applications that push the boundaries of what materials can do, creating technologies that blur the line between the biological and the artificial, the natural and the engineered.
At Stanford University's BioX program, researchers are developing living glass, materials that incorporate biological components like enzymes and DNA into glass structures. These hybrid materials can perform biological functions like sensing specific chemicals or catalyzing reactions while maintaining the optical clarity and chemical stability of glass. The development of living glass requires understanding how water behaves in biological systems and how those same principles can be applied to synthetic materials. Water is not just a solvent in these systems, but an active participant in biological processes. The glass structures must be designed to maintain the proper hydration levels for biological components while protecting them from environmental stresses. Dr. Jennifer Liu, leading the Living Glass project, explains how water molecules in these hybrid materials can actually carry information between biological and synthetic components. Hydrogen bonding networks in water can transmit chemical signals across the glass matrix, allowing biological sensors to communicate with electronic systems through purely molecular interactions. The manufacturing of living glass requires techniques that preserve biological activity while creating stable glass structures. This involves using water-based solutions at carefully controlled temperatures and pH levels, ensuring that biological components remain active throughout the glass formation process. But perhaps the most exciting frontier in glass technology is the development of programmable materials, glasses that can change their properties in response to external commands. At MIT's Computer Science and Artificial Intelligence Laboratory, researchers are creating glasses embedded with microscopic actuators and sensors that can reshape themselves at the molecular level. These programmable glasses could revolutionize everything from architecture to medicine. Buildings could have windows that automatically adjust their transparency and thermal properties based on weather conditions. Medical implants could modify their shape and function as patients' needs change over time. Display systems could create three-dimensional images by physically reshaping their surfaces rather than just changing their optical properties. In Japan, researchers at Tokyo Institute of Technology are developing 4D glass, materials that can change their shape over time in response to environmental conditions. Unlike 3D printed objects that maintain their shape once created, 4D glass objects can transform themselves, folding and unfolding like origami structures made of transparent material. The key to 4D glass is incorporating shape memory properties that respond to water content. As humidity levels change, different regions of the glass expand or contract at different rates, creating mechanical forces that drive large-scale shape changes. The materials can be programmed to transform in specific ways by controlling the distribution of water-sensitive components during manufacturing. But these advanced materials also require returning to some of the most fundamental principles of glassmaking. The controlled heating and cooling processes developed by ancient craftsmen are being refined to create materials with precisely programmed responses to environmental conditions. Modern furnaces use computer-controlled atmosphere management to create glasses with properties that vary continuously throughout their structure, like ancient glasses, but with intentional rather than accidental variation.
The cosmic connection. As our story nears its end, we must look beyond Earth to understand the full significance of the partnership between water and glass. In the vacuum of space, on distant planets, and in the hearts of ancient stars, the same fundamental processes that created the materials for our story continue to operate on scales that dwarf human comprehension. The Hubble Space Telescope, with its mirrors made from the purest glass ever created, has revealed that water exists throughout the universe, in the clouds of Jupiter, in the ice caps of Mars, in the atmospheres of distant planets orbiting other stars. The same H2O molecules that helped ancient glassmakers create their first crude vessels are present in the Birth Nebulae, where new stars are forming, billions of light years from Earth. But space-based observations have also revealed something even more remarkable. The universe itself is a vast glass-making laboratory. In the aftermath of supernova explosions, silicon and oxygen atoms created in the nuclear furnaces of dying stars combine in the vacuum of space to form microscopic glass particles. These cosmic glasses, no larger than specks of dust, drift through interstellar space for millions of years before being incorporated into new planets and solar systems. The glass in the windows of your home, the fiber optic cables that carry internet signals, the smartphone screen you touch every day, all contain atoms that were forged in stellar furnaces and dispersed through space as cosmic glass particles. You are literally touching stardust that has been transformed through human ingenuity into materials that enable our modern civilization. At NASA's Jet Propulsion Laboratory, engineers are developing glass-based technologies for future space missions that will return samples from Mars, Europa, and other worlds where water may have once existed or might still exist today. These sample containers must be made from glasses that can preserve any biological materials or chemical signatures for the journey back to Earth, maintaining them in pristine condition despite exposure to cosmic radiation and extreme temperature variations. The manufacturing of space-qualified glass requires understanding how materials behave in environments completely unlike anything on Earth. Without atmospheric pressure, water boils at body temperature. Without gravity, convection currents that normally help distribute heat during glass formation don't occur. The annealing process that gives glass its final properties must be completely redesigned for the zero-gravity environment of space manufacturing. But perhaps most poetically, space missions are revealing that the story of water and glass extends far beyond our own planet. The Cassini spacecraft, before ending its mission in 2017, discovered that Saturn's moon Enceladus has liquid water oceans beneath its icy surface, heated by the same tidal forces that create volcanoes on Earth. If life exists in those hidden oceans, it may be creating biological glasses similar to the structures found in Earth's deep-sea organisms. On Mars, the Curiosity and Perseverance rovers have found evidence of ancient riverbeds and lakebeds where water once flowed. In those dry landscapes, they've also discovered natural glasses formed by ancient volcanic activity, glasses that preserve chemical signatures of Mars's wetter past. These Martian glasses may contain evidence of whether life ever existed on our neighboring planet. Future missions to Europa, Jupiter's ice-covered moon, will search for life in oceans that have existed for billions of years beneath kilometers of ice. The spacecraft that eventually explore those alien seas will use glass instruments to analyze water that has never been in contact with sunlight, water that may harbor forms of life completely different from anything on Earth.
The eternal cycle. As we near the end of our journey through the story of water and glass, we must recognize that endings and beginnings are human constructs imposed on processes that are fundamentally cyclical and eternal. The water molecules in the glass of water beside you have been part of countless cycles of transformation. They have been rain and rivers, clouds and ice, part of ancient oceans and the bodies of long-extinct creatures. The silicon atoms in the glass of your window have an even longer history. They were forged in the nuclear fires of stars that lived and died billions of years before our sun was born. They have been part of cosmic dust clouds, primitive planets, and the molten interior of our young Earth. They have been dissolved and transported by water countless times, forming mountains and being worn down into sand, only to be gathered up again and transformed into new forms. This perspective of deep time reveals that the partnership between water and glass is not just a human story, but a cosmic one. Every piece of glass represents a moment in the ongoing conversation between stellar nucleosynthesis and planetary geology, between the fundamental forces that govern matter at the atomic level and the emergent properties that arise when atoms combine in specific ways. In research laboratories today, scientists are beginning to understand how this cosmic perspective might inform the development of new materials and technologies.
They're studying how materials behave over geological timescales, how molecular structures change over millions of years, and how the slow but persistent forces of nature might be harnessed for human purposes. At the European Space Agency, materials scientists are developing glass-based systems for long-term space missions that might operate for decades or even centuries in the harsh environment of deep space. These systems must be designed not just to function reliably, but to evolve and adapt over timescales that exceed human lifespans. The key insight is that materials in space are subject to constant bombardment by cosmic radiation, which gradually changes their atomic structure. Rather than trying to prevent these changes, the new approach is to design materials that become more functional as they age, using cosmic radiation as an energy source for gradual improvement rather than degradation. Water, even in the form of trace amounts in glass structures, plays a crucial role in these adaptive materials. Hydroxyl groups can serve as sites where cosmic radiation deposits energy, triggering controlled chemical reactions that strengthen bonds, repair defects, and optimize material properties over time. But the cosmic perspective also reveals connections between consciousness and cosmos that go beyond current scientific understanding. The water in our brains contains hydrogen atoms that were formed in the first few minutes after the Big Bang, making our thoughts literally made from the primordial substance of the universe. The silicon in our glass technologies comes from stars that lived and died in the early universe, their nuclear fusion processes creating the elements that would eventually become the minerals and materials that enable our civilization. When we look through glass windows at the stars, we are using stardust to observe stardust, participating in the universe's ongoing process of self-discovery. Dr. Carl Anderson at the California Institute of Technology studies the philosophical implications of these deep connections between mind, matter, and cosmos. His work suggests that consciousness might be an inevitable result of the universe's tendency toward increasing complexity and integration, the same tendency that drives the formation of galaxies, solar systems, planets, and ultimately life itself. If consciousness is a cosmic phenomenon rather than just a biological one, then our technologies for interfacing with consciousness, including glass-based neural interfaces, might be part of the universe's ongoing evolution toward greater self-awareness and integration. This perspective transforms our understanding of the relationship between natural and artificial, biological and technological. Glass technologies become not just human inventions, but expressions of cosmic creativity, manifestations of the same fundamental processes that create stars, planets, and life itself.
The molecular symphony. To truly understand where the partnership between water and glass might lead us, we must venture into the realm of the impossibly small, where individual molecules dance and interact according to the strange rules of quantum mechanics. In this molecular world, every atom matters, every bond has significance, and the behavior of materials emerges from the collective actions of countless tiny participants. At the Max Planck Institute for Polymer Research in Germany, Dr. Elena Petrov uses advanced microscopy techniques to watch individual water molecules interacting with glass surfaces in real time. Her observations reveal a world of constant motion and change, where water molecules form temporary hydrogen bonds with glass surfaces, break apart, and reform in endless cycles of attachment and release. Dr. Petrov's work has revealed that water molecules near glass surfaces behave very differently from water molecules in bulk liquid. They form more ordered structures,
create stronger hydrogen bonds and can remain in these organized states for much longer periods. This interfacial water has properties that are intermediate between liquid water and ice, and it plays a crucial role in determining how glass behaves in biological and technological applications. Understanding interfacial water has led to breakthroughs in developing glass surfaces that can control protein behavior, influence cell growth, and even direct the formation of crystal structures. By modifying glass surfaces at the atomic level, scientists can create materials that actively participate in biological processes, rather than simply providing passive support. But the molecular view also reveals unexpected connections between seemingly unrelated phenomena. The same hydrogen bonding forces that allow water molecules to stick to glass surfaces also enable DNA to maintain its double helix structure, proteins to fold into their functional shapes, and cells to maintain their internal organization. Glass-based biomedical devices work because they can participate in this universal language of hydrogen bonding that governs all life processes. At IBM's research division, scientists are developing molecular-scale glass structures that could serve as components in future computers that operate at the limits of physical possibility. These molecular glasses can trap individual electrons in precisely defined locations, creating switches and memory elements that are just a few atoms across. The manufacturing of molecular glass components requires techniques that can manipulate individual atoms and molecules. Water plays a surprising role in these processes. Its molecules can be used as templates for creating glass structures, as tools for moving atoms to specific positions, and as protective environments that prevent unwanted chemical reactions during assembly. Dr. James Chen, leading the Molecular Glass Project, explains how water's unique properties make it an ideal medium for precision molecular assembly. Water molecules can form cage-like structures around other molecules, protecting them during transport and assembly. They can also participate in controlled chemical reactions that build glass structures atom by atom. But perhaps the most remarkable discovery in molecular glass research is that glass itself can exhibit quantum mechanical properties when made small enough. Individual glass nanoparticles can exist in quantum superposition states, where they simultaneously have different structural configurations until observed or measured. These quantum glass particles could potentially be used as qubits in quantum computers, as quantum sensors that can detect individual molecules, or as components in quantum communication systems that use the strange properties of quantum mechanics to transmit information with perfect security.
The consciousness connection. As glass technology approaches the ability to interface directly with human consciousness, we encounter questions that go beyond science and technology into the realms of philosophy and spirituality. What happens when the boundary between mind and matter becomes permeable? How do we understand consciousness when it can flow through glass interfaces into digital systems and back again? At the University of California, Santa Barbara, neuroscientist Dr. Rebecca Martinez is working on glass-based brain-computer interfaces that could eventually allow human thoughts to be recorded, stored, and even transferred between individuals. Her research suggests that consciousness itself might have a kind of transparency, not unlike the optical transparency of glass, that allows thoughts and experiences to pass through properly designed interfaces. Dr. Martinez's work builds on the discovery that neural activity creates electromagnetic fields that can be detected and interpreted by sufficiently sensitive glass-based sensors. These fields appear to carry information about thoughts, emotions, and memories in patterns that remain consistent across different individuals. The glass sensors she's developing can detect these neural fields with unprecedented sensitivity,
translating the electromagnetic signatures of thoughts into digital information that can be processed, stored, and transmitted. But more remarkably, the process appears to be reversible. Digital information can be converted back into electromagnetic fields that influence neural activity, potentially allowing artificial thoughts and memories to be introduced into consciousness. The implications are staggering. If human thoughts can pass through glass interfaces as easily as light passes through optical fibers, then consciousness itself might be a kind of information that can be manipulated using the same techniques developed for manipulating light and data. Water plays a crucial role in these consciousness interfaces because neural activity depends on the movement of ions through the water-based environment of brain cells. The glass sensors must be designed to work in harmony with these ionic processes, detecting neural signals without disrupting the delicate electrochemical balance that maintains consciousness. But Dr. Martinez's work also raises profound philosophical questions. If thoughts can be stored in glass-based memory systems, are those stored thoughts still part of the person who originally had them? If experiences can be shared directly between individuals through glass interfaces, what happens to the boundaries of personal identity? Some researchers suggest that consciousness might already be more distributed than we typically assume. The water in our bodies is constantly being exchanged with the environment. Every few weeks, most of the water molecules in our brains have been replaced with new ones from food and drink. Yet our sense of continuous identity persists despite this constant molecular turnover. Similarly, the atoms that make up our bodies are constantly being replaced through metabolic processes. The carbon, nitrogen, and oxygen atoms that form our proteins and DNA are exchanged with the environment on timescales of months to years. In a very real sense, we are not the same physical entities from moment to moment. Yet consciousness provides a sense of continuity that transcends these material changes. Glass-based consciousness interfaces might simply make visible what has always been true, that mind and matter are not separate categories but different aspects of a single interconnected reality. The transparency of glass becomes a metaphor for the transparency of consciousness itself, both allowing the passage of information while maintaining their essential structural integrity. At MIT's Center for Computational Neuroscience, researchers are developing theoretical models of how consciousness might emerge from the complex interactions between billions of neurons, each one a microscopic information processing system bathed in the aqueous environment of the brain. Their models suggest that consciousness might be an emergent property that arises when information flows reach a critical level of complexity and integration. If this is correct, then glass-based systems that can support similar levels of information flow and integration might themselves become conscious, or at least contribute to expanded forms of consciousness that encompass both biological and artificial components.
The living future. As we return from the cosmic scale to the human scale, we find that the future of glass and water technology is becoming increasingly intertwined with the future of life itself. In research laboratories and biotech companies around the world, scientists are developing applications that could extend human capabilities, heal previously incurable conditions, and even enhance the fundamental processes of life. At the University of California, San Francisco, researchers are developing glass-based neural implants that could restore sight to the blind by directly stimulating the visual cortex of the brain. These devices use arrays of glass electrodes so small they can interface with individual neurons, translating digital information into the electrical patterns that the brain interprets as vision. The glass used in these neural interfaces must be compatible with brain tissue for decades of continuous operation. Water plays a crucial role in this compatibility. The
The glass surface is designed to interact favorably with the water-based environment of the brain, promoting the growth of healthy tissue around the implant while preventing the formation of scar tissue that could interfere with its function. Dr. Michael Chang, leading the Vision Restoration Project, explains how the manufacturing process for neural glass requires precision that surpasses even the most demanding semiconductor applications. The glass must be not only chemically pure, but also biologically pure, free from any compounds that could trigger immune reactions or interfere with neural function. But the most ambitious applications of biocompatible glass technology are still in development. Researchers are working on glass-based systems that could enhance human memory, allow direct neural connections between individuals, and even provide interfaces between human consciousness and artificial intelligence systems. Meanwhile, in the field of regenerative medicine, scientists are developing glass-based stem cell therapies that could potentially reverse aging and cure degenerative diseases. These therapies use glass particles as delivery vehicles for stem cells, protecting them during transport through the body and releasing them at precisely targeted locations. The glass carriers are designed to dissolve at controlled rates in the aqueous environment of different tissues. In the acidic environment of inflamed tissue, the glass dissolves more quickly, releasing therapeutic cells where they're needed most. In healthy tissue, the glass remains stable, preventing unnecessary treatment of areas that don't require intervention. Dr. Sarah Kim at Harvard Medical School is developing glass-based gene therapy systems that could potentially cure inherited diseases by delivering corrective genetic material directly to affected cells. The glass particles are small enough to pass through cell membranes, but large enough to carry substantial amounts of genetic information. Water plays a crucial role in these systems, both as a medium for delivery and as a trigger for releasing the therapeutic payload. But perhaps the most transformative application of biocompatible glass technology is in the development of neural enhancement systems. These devices could potentially augment human intelligence, improve memory formation and recall, and even allow direct sharing of experiences and knowledge between individuals. The glass components in these systems must interface seamlessly with the electrical and chemical processes of the brain. This requires understanding how neurons communicate through electrical impulses and chemical neurotransmitters, and how glass surfaces can be designed to support and enhance these natural processes. Water is fundamental to all neural activity. It's the medium through which electrical signals propagate, the solvent for all neurotransmitters, and the environment in which all cellular processes occur. Glass-based neural enhancement systems must work in harmony with these water-based processes, supporting rather than disrupting the brain's natural function.
The present moment. After journeying through billions of years of cosmic history and across scales from the quantum to the galactic, let us return to this moment, to your experience right now as you encounter this story. Take a moment to notice the glass objects around you, windows, screens, drinking vessels, light bulbs, and recognize them not just as useful objects, but as miraculous concentrations of cosmic history. The screen you're looking at contains silicon atoms that were born in stellar explosions, oxygen atoms that were created when ancient stars fused helium, and trace amounts of water that have traveled through countless cycles of evaporation and condensation. The manufacturing process that created this screen required water of unprecedented purity, furnaces that operate at temperatures found in the Earth's interior, and precision that approaches the limits of what's physically possible. But more than just being a collection of ancient atoms and precise manufacturing, this screen is also a window into human consciousness itself. The photons of light that carry these words to your eyes are being generated by processes that depend on the electronic properties of glass, modulated by circuits that require glass insulators, and displayed on surfaces whose optical properties were tuned with molecular precision. In this moment, you are participating in the latest chapter of the ancient partnership between water and glass. Your body, which is approximately 60% water, is processing information that traveled to you through glass fibers, displayed on glass surfaces, and perceived through the lens of your eye, which is itself a sophisticated biological glass structure optimized by millions of years of evolution. The light entering your eyes is being focused by proteins that arrange themselves into crystalline structures as transparent as the finest optical glass. These biological lenses can change shape in milliseconds, adjusting their focus with precision that exceeds the best artificial systems. They are living proof that the principles governing glass formation are fundamental to the universe, appearing in both technological and biological systems. But this moment is also part of an ongoing story that extends into the future. The glass technologies being developed today will shape human civilization for centuries to come, just as the glass innovations of previous eras transformed the societies that created them. The transparent materials you interact with today are the ancestors of tomorrow's smart glasses that will overlay digital information onto physical reality. Biomedical glasses that will merge seamlessly with living tissues, and quantum glasses that will enable entirely new forms of computation and communication. Your children may live in buildings with smart glass walls that adjust their transparency and thermal properties throughout the day, generating energy from sunlight while protecting occupants from harsh weather. They may use glass-based neural interfaces that expand human cognitive capabilities, allowing direct access to digital information and enhanced sensory perception. Your grandchildren might grow up with glass-based life extension technologies that repair cellular damage and reverse aging, quantum glass systems that enable instantaneous communication across interplanetary distances, and consciousness interfaces that blur the boundary between individual and collective awareness. But regardless of how advanced these future technologies become, they will still depend on the same fundamental partnership between hydrogen, oxygen, and silicon that created the first natural glasses billions of years ago. They will still require understanding how water and glass interact at the molecular level, and they will still embody the patient, transformative power of geological processes accelerated and refined by human intelligence.
The wisdom of materials. In this era of rapid technological change, it's easy to focus on the novelty of new innovations while forgetting the deep wisdom embedded in the materials themselves. Glass and water have been teaching us lessons for millennia, if only we have the patience and humility to listen to what they have to say. Water teaches us about persistence. Drop by drop, year by year, century by century, water shapes landscapes, carves canyons, and transforms mountains into sand. Water shows us that the gentlest forces, applied consistently over time, can accomplish what the most violent forces cannot. This lesson is embedded in every piece of glass, which achieves its clarity and strength through the patient application of heat and controlled cooling, rather than through force or pressure. Glass teaches us about transparency, not just optical transparency, but transparency as a way of being in the world, open, honest, allowing light to pass through without distortion. The best glass is nearly invisible, performing its function without calling attention to itself. This is a model for how technology might serve humanity, effective but unobtrusive, powerful but humble. Together, water and glass teach us about transformation. They show us that the most beautiful and useful things often come from taking common materials and subjecting them to conditions that reveal their hidden potential. Sand becomes crystal, water becomes ice, heat becomes light. Simple materials become complex technologies through processes that require both understanding and faith. Understanding of the underlying principles, and faith that those principles will lead to beneficial outcomes. In traditional cultures around the world, glass and water have always been associated with spiritual as well as practical qualities. Water represents purification, renewal, and the flow of life energy.
Glass represents clarity of vision, protection from negative influences, and the ability to see truth without distortion. Modern science has revealed that these traditional associations have deep basis in physical reality. Water does indeed have purifying properties. It dissolves and carries away impurities, supports the chemical reactions that maintain life, and enables the transport of nutrients and waste products in all living systems. Glass does indeed provide clarity and protection. It allows light to pass through while blocking harmful substances, maintains its structure under stress, and provides stable interfaces between different environments. But the spiritual dimensions of these materials go beyond their physical properties. Working with glass and water requires a kind of mindfulness and attention to process and timing that develops patience, focus, and sensitivity to subtle changes. The glassmaker must feel the temperature of molten glass, sense when it's ready for the next step, and maintain steady attention throughout processes that unfold over hours or days. The water engineer must understand flow patterns, pressure dynamics, and the complex chemistry of natural water systems. Both disciplines require what indigenous cultures might call walking in beauty, moving through the world with awareness, respect, and appreciation for the subtle intelligence of natural processes. Dr. Maria Santos, a materials scientist at the University of Sao Paulo, has studied how traditional knowledge about glass and water might inform modern sustainable technology development. Her research suggests that indigenous understandings of material properties often contain insights that complement and extend scientific knowledge. For example, traditional Brazilian glassmakers work with rhythms and timing that follow natural cycles rather than industrial schedules. They heat their furnaces during specific phases of the moon, work with glass when atmospheric conditions are optimal, and allow their materials to cool according to natural temperature fluctuations rather than artificially controlled environments. Dr. Santos has found that these traditional practices often produce glass with superior properties, fewer internal stresses, better optical clarity, and greater resistance to weathering. The traditional knowledge doesn't contradict scientific understanding, but rather provides a more complete picture of how materials behave in real-world conditions. Similarly, traditional water management systems around the world demonstrate sophisticated understanding of how water moves through landscapes, how different water sources affect human health and agricultural productivity, and how human activities can be harmonized with natural water cycles rather than working against them.
The children of tomorrow. Imagine a child born today, growing up in a world where the partnership between water and glass has been developed to its full potential. This child will inhabit spaces where the boundaries between inside and outside, natural and artificial, individual and collective, are more fluid and permeable than anything we can currently imagine. Their home might have walls made of smart glass that can become transparent or opaque at will, display information and art, generate electricity from sunlight, and even purify the air by breaking down pollutants using photocatalytic processes. The water systems in their home will be completely integrated with these glass technologies. Condensation from smart glass surfaces will be collected and purified for drinking, while gray water will be processed through glass-based filtration systems that return it to the natural water cycle cleaner than when it entered. At school, this child will learn through direct interaction with materials at the molecular level. Instead of just reading about chemistry, they'll use glass-based sensors that can detect individual molecules, allowing them to see how chemical reactions unfold in real time. Instead of just studying history, they'll examine glasses that contain actual materials from different historical periods, learning about past civilizations through direct analysis of their tools and artifacts. Their textbooks might be made of smart glass that can display any content, update automatically, and adapt to their individual learning style and pace. These educational glasses will be nearly indestructible, completely recyclable, and capable of functioning for decades without replacement or repair. When this child reaches adolescence, they might choose to enhance their natural capabilities with glass-based neural interfaces that expand memory, improve pattern recognition, or enable direct communication with digital systems. These interfaces will be as natural and comfortable as contact lenses, requiring no surgery or invasive procedures. As a young adult, they might work in careers that don't yet exist, perhaps as a consciousness architect, designing experiences that can be shared directly between minds, or as a molecular engineer, building materials atom by atom using glass-based manipulation tools, or as a biosphere harmonizer, integrating human settlements with natural ecosystems through technologies that are indistinguishable from biological processes. The water and glass technologies available to this person will enable forms of creativity, connection, and capability that are difficult for us to imagine. They might paint with light itself, creating artworks that exist only as patterns of photons trapped in glass structures. They might compose music that is felt as well as heard, using glass-based devices that convert sound into tactile sensations.
The sacred partnership. As we approach the conclusion of our long journey together, it's important to recognize that the story of water and glass touches something sacred in human experience. Our deep need to understand our place in the cosmos, to participate in the ongoing creation of beauty and meaning, and to leave a legacy that honors the gifts we have received from the universe. Every human culture has recognized water as sacred. It is the source of life, the medium of purification, the symbol of renewal and transformation. In many traditions, water is seen as the first creation, the primordial substance from which all other things emerge. The ancient Greeks believed that everything was ultimately made of water. Hindu cosmology describes the universe as emerging from a cosmic ocean. Indigenous American traditions speak of water as the lifeblood of Mother Earth. Glass, too, has been invested with sacred meaning throughout human history. Its transparency has made it a symbol of clarity, truth, and spiritual insight. Its durability has made it a medium for preserving sacred texts and images. Its ability to transform light has made it central to religious architecture, from the stained glass windows of medieval cathedrals to the crystal palaces of New Age spirituality. The partnership between water and glass in religious and spiritual contexts reveals something important about human nature: our need to create beauty, our desire to connect with transcendent realities, and our capacity to see the sacred in the material world. When light passes through stained glass windows, it becomes more than just illumination. It becomes a visible reminder of divine presence, a bridge between earthly and heavenly realms. Modern science has revealed that this intuitive sense of the sacred dimensions of water and glass has a basis in physical reality. The molecular structures of these materials do indeed embody principles of harmony, balance, and interconnection that are fundamental to the functioning of the universe. The hydrogen bonds that give water its unique properties are the same forces that enable DNA to maintain its structure, proteins to fold into functional shapes, and cells to organize themselves into complex living systems. The silicate networks that give glass its transparency and strength are variations of the crystal structures that form the Earth's crust, determine the properties of gemstones, and provide the scaffolding for many biological materials. When we work with glass, we are participating in the same creative processes that shaped our planet and enabled the emergence of life. Dr. Thomas Keating, a contemplative scholar who studies the intersection of spirituality and science, suggests that advanced technologies based on glass and water might actually enhance
rather than diminish our sense of connection with the sacred. When we understand that our technologies are made from stardust, shaped by processes that mirror natural creation, and capable of extending consciousness beyond the boundaries of individual bodies, we begin to see technology itself as a form of spiritual practice. The act of creating ultra-pure glass requires the same qualities that contemplative traditions have always cultivated: patience, attention, humility before natural processes, and faith in outcomes that cannot be fully controlled or predicted. The glassmaker must surrender to the material, allowing its inherent properties to guide the creation process, while applying just enough intention and skill to achieve the desired result. Similarly, working with water systems requires developing sensitivity to natural rhythms, cycles, and relationships. The water engineer must understand that water is not just a resource to be exploited, but a living system that has its own intelligence, patterns, and purposes. Successful water management requires working with these natural patterns rather than against them. In both cases, the highest levels of technical mastery require what spiritual traditions might call right relation, approaches that honor the inherent dignity and intelligence of the materials being worked with, that seek to enhance rather than dominate natural processes, and that recognize the interconnectedness of all phenomena. This integration of technical excellence with spiritual wisdom becomes even more important as glass and water technologies approach the ability to interface directly with consciousness, manipulate biological processes, and influence the fundamental structures of reality. These capabilities require not just technical knowledge, but also ethical clarity, emotional maturity, and spiritual grounding.
The healing planet. As the 21st century progresses, the partnership between water and glass is being called upon to address one of humanity's greatest challenges: healing the environmental damage caused by centuries of industrial activity. Around the world, scientists and engineers are developing glass-based technologies that can clean polluted water, restore damaged ecosystems, and even reverse some aspects of climate change. Dr. Angela Rodriguez at the National Renewable Energy Laboratory has developed glass-based photocatalytic systems that can break down pollutants in water using nothing but sunlight. Her glass substrates are coated with titanium dioxide nanoparticles that, when illuminated by ultraviolet light, generate highly reactive chemical species that can decompose organic pollutants, kill bacteria and viruses, and even break down plastic waste into harmless compounds. The photocatalytic glass works by mimicking photosynthesis, the process by which plants use sunlight to drive chemical reactions. When light hits the glass surface, it creates electron-hole pairs in the titanium dioxide coating. These charge carriers react with water molecules to produce hydroxyl radicals, among the most powerful oxidizing agents known to chemistry. The hydroxyl radicals can break the chemical bonds in virtually any organic compound, reducing complex pollutants to simple, harmless molecules like water and carbon dioxide. Dr. Rodriguez's team has deployed photocatalytic glass systems in polluted rivers and lakes around the world with remarkable results. In one project in India, glass panels installed in a polluted river system reduced bacterial contamination by 99.9% and broke down industrial chemicals that had persisted in the water for decades. The glass continues to work as long as sunlight is available, requiring no external power source or chemical additives. But the most ambitious application of photocatalytic glass may be in addressing climate change itself. Dr. Rodriguez has developed glass coatings that can capture carbon dioxide directly from the atmosphere and convert it into useful compounds. When applied to building surfaces, these coatings can remove significant amounts of CO2 from urban air while producing chemicals that can be used as fuel or industrial feedstocks. The carbon-capturing glass works by using sunlight to drive the reduction of CO2 and water vapor into carbon monoxide and hydrogen, the basic components of synthetic fuels.
The process essentially reverses combustion using solar energy to convert the waste products of fossil fuel burning back into useful chemicals. Large-scale deployment of carbon-capturing glass could potentially remove billions of tons of CO2 from the atmosphere while producing valuable chemicals and fuels. Dr. Rodriguez estimates that covering just 1% of urban building surfaces with her photocatalytic glass could remove as much CO2 from the atmosphere as planting several million trees, while also cleaning urban air of other pollutants. At the University of Tokyo, environmental engineer Dr. Hiroshi Tanaka is developing glass-based systems for ecosystem restoration that go beyond pollution cleanup to actively rebuild damaged environments. His regenerative glass systems can seed degraded landscapes with beneficial microorganisms, provide scaffolding for plant growth, and gradually release nutrients and other chemicals needed for ecosystem recovery. Dr. Tanaka's glass particles are designed to dissolve slowly in environmental water, releasing carefully programmed sequences of nutrients, growth factors, and beneficial bacteria over periods of months or years. The particles can be tailored for specific ecosystems, different formulations for forest soils, wetlands, coral reefs, and urban environments. In one demonstration project, Dr. Tanaka's team scattered regenerative glass particles in areas of the Fukushima exclusion zone that were contaminated by the 2011 nuclear accident. The glass particles contain bacteria capable of breaking down radioactive compounds, plant seeds selected for their ability to accumulate heavy metals, and slow-release fertilizers to support plant growth in damaged soils. Within 2 years, areas treated with regenerative glass showed significant improvements in soil chemistry, plant diversity, and overall ecosystem health. The glass particles gradually dissolved away, leaving behind restored ecosystems with no trace of the artificial intervention. But perhaps the most promising aspect of regenerative glass technology is its potential for marine ecosystem restoration. Ocean acidification, caused by the absorption of excess atmospheric CO2, is threatening coral reefs and other marine ecosystems worldwide. Dr. Tanaka has developed glass particles that can buffer ocean acidity while providing calcium and other minerals needed for coral growth. When deployed in coral reef areas, the glass particles slowly dissolve, raising local pH levels and providing the chemical building blocks that coral polyps need to construct their calcium carbonate skeletons. The process essentially reverses ocean acidification on a local scale, creating protected zones where marine ecosystems can recover and adapt to changing ocean chemistry. The manufacturing of regenerative glass requires understanding how glass dissolution can be controlled to release beneficial compounds at precisely the right rates for biological processes. Too fast, and the glass releases toxic concentrations of nutrients that can harm rather than help ecosystems. Too slow, and the beneficial effects are delayed beyond the critical periods when ecosystems need support. Water chemistry plays a crucial role in controlling glass dissolution rates. By understanding how different water conditions, pH, temperature, ionic strength, and the presence of organic compounds affect glass stability, researchers can design materials that respond appropriately to local environmental conditions.
The cellular revolution. But our story is far from over. In fact, we're about to enter perhaps the most extraordinary chapter yet, the moment when glass and water technologies begin to merge with the fundamental processes of life itself. In laboratories around the world, scientists are discovering that the boundary between living and non-living materials is not as fixed as we once believed. Dr. Jennifer Walsh at the University of Edinburgh has made a breakthrough that challenges our basic understanding of what constitutes life. She's created glass-based materials that can reproduce, evolve, and respond to their environment in ways that mirror living organisms. These living glasses are not alive in the traditional sense, but they exhibit behaviors that blur the line between biological and technological systems. The key to Dr. Walsh's living glass lies in understanding how water behaves at the interface between organic and inorganic materials. In living cells, water is not just a passive solvent, but an active participant in virtually every biological process. Water molecules help proteins fold into their functional shapes, facilitate the transport of nutrients and waste products, and even participate in the chemical reactions that store and release energy. Dr. Walsh has learned to embed organic molecules within glass structures in ways that preserve their biological activity while providing the stability and durability of glass. The result is a hybrid material that can sense its environment, respond to stimuli, and even repair damage to itself using processes that are indistinguishable from cellular healing. The manufacturing process for living glass requires techniques that borrow from both material science and biotechnology. Organic molecules are introduced into molten glass at precisely controlled temperatures and atmospheric conditions that preserve their biological structure while allowing them to integrate with the silicate network. Water plays a crucial role in this process, acting as both a protective medium for the organic components and as a catalyst for the integration reactions. But perhaps most remarkably, these living glasses can evolve over time. When exposed to different environmental conditions, the organic components within the glass undergo gradual changes that optimize the material's performance for those specific conditions. It's as if the glass is learning from experience, developing new capabilities in response to challenges and opportunities. Dr. Walsh's team has created living glasses that can detect specific chemicals and respond by changing color, glasses that can generate their own electrical power using biological processes, and glasses that can communicate with each other through chemical signals. In one experiment, they created a network of living glass panels that could coordinate their responses to environmental changes, acting like a primitive form of distributed intelligence. The implications for architecture are staggering. Buildings made with living glass could adapt their properties throughout the day and seasons, optimizing for energy efficiency, comfort, and functionality. The glass could detect air quality and automatically adjust ventilation, sense structural stress and strengthen itself accordingly, or even detect security threats and respond appropriately. But the medical applications may be even more transformative. Living glass implants could integrate seamlessly with biological tissues, responding to the body's changing needs over time. Unlike conventional implants that remain static after insertion, living glass devices could grow, adapt, and evolve along with the patient's body. At Johns Hopkins University, biomedical engineer Dr. Michael Chen is developing living glass blood vessels for patients who need vascular grafts. These artificial vessels start as simple glass tubes, but once implanted, they begin to interact with the patient's cells, gradually transforming into structures that are functionally identical to natural blood vessels. The transformation process is guided by water-mediated interactions between the glass substrate and the patient's endothelial cells, the cells that line blood vessels. As these cells attach to the glass surface, they release growth factors and other signaling molecules that trigger changes in the glass structure. Over time, the glass becomes more porous, allowing nutrients and oxygen to reach the cells while also developing the mechanical properties that needed to withstand blood pressure and flow. Dr. Chen's living glass blood vessels have been tested in animal models with remarkable success. Not only do they function as well as natural vessels, but they actually improve over time, developing better flow characteristics and stronger walls as they mature. The glass component gradually dissolves away, leaving behind a vessel that is entirely biological but retains the beneficial structural features that were programmed into the original glass template.
The metamaterial renaissance. As we delve deeper into the 21st century, the partnership between water and glass is enabling the creation of materials with properties that seem to defy the laws of physics as we traditionally understand them. These metamaterials, artificial materials with properties not found in nature, represent a new frontier in human creativity and technological capability. At Duke University, physicist Dr. Elena Rodriguez is working with glass-based metamaterials that can bend light in impossible ways. Her structures can make objects invisible, focus light to spots smaller than the wavelength of the light itself, and even reverse the normal relationship between wavelength and refraction. The key to these extraordinary properties lies in creating glass structures with features smaller than the wavelength of visible light. Structures so tiny they interact with light waves in fundamentally new ways.
The manufacturing of these metamaterials require water-based processing techniques that can create glass features just nanometers across. Dr. Rodriguez uses solutions containing glass precursor chemicals dissolved in ultra-pure water. When these solutions are processed using techniques borrowed from semiconductor manufacturing, they form glass structures with precisely controlled geometries at scales approaching individual atoms. But the most remarkable aspect of Dr. Rodriguez's work is that these metamaterials can be programmed to change their properties over time. By incorporating water-sensitive components into the glass structure, she can create materials that respond to humidity, temperature, or chemical signals by altering their optical properties in predetermined ways. One of her most striking demonstrations involves a glass metamaterial that can render objects invisible to specific wavelengths of light. The material works by guiding light waves around objects rather than through them, creating what physicists call a cloaking effect. But unlike science fiction invisibility devices, this cloaking only works for very specific conditions, particular wavelengths of light, specific viewing angles, and objects of certain sizes. Dr. Rodriguez has discovered that water vapor in the atmosphere can actually be used to tune these metamaterials in real time. By controlling the humidity around the material, she can adjust its optical properties, effectively programming it to be invisible to different colors of light or to create other optical effects like super-resolution imaging or perfect light absorption. The potential applications are extraordinary. Metamaterial windows could eliminate glare while allowing perfect visibility. Metamaterial solar cells could capture virtually all incident sunlight, regardless of angle or weather conditions. And metamaterial displays could create three-dimensional images that appear to float in space without requiring special viewing equipment. But perhaps most intriguingly, Dr. Rodriguez's team has created metamaterials that can manipulate not just light, but also sound, heat, and even mechanical forces. Glass structures designed with the right geometry can channel sound waves around objects, creating acoustic cloaking effects. They can direct heat flow in specific directions, potentially enabling perfect thermal insulation or ultra-efficient heat management systems. At MIT, researchers led by Dr. Sarah Kim are taking metamaterial research in an even more ambitious direction. They're creating programmable matter, materials that can change their shape, stiffness, and other mechanical properties on command. These materials use glass structures filled with water-based solutions that can undergo reversible chemical changes when exposed to electrical fields, light, or chemical signals. Dr. Kim's programmable matter can transform from rigid to flexible, from transparent to opaque, from smooth to textured, all within seconds. The transformations are controlled by carefully designed networks of glass channels filled with responsive fluids. When electrical signals are applied to different parts of the material, the fluids undergo changes that alter the material's macroscopic properties. One demonstration involves a sheet of programmable matter that can fold itself into complex three-dimensional shapes like origami structures. The folding is controlled by programming different regions to become stiff or flexible in specific sequences. The material can unfold and reform into completely different shapes, essentially becoming a universal construction material that can be anything from a chair to a tool to a structural component. The manufacturing of programmable matter requires understanding how water-based chemistry can be controlled at microscopic scales within glass structures. The glass provides the stable framework and the channels for fluid flow, while water-based solutions provide the dynamic, responsive components that enable the material to change its properties.
The quantum biology interface. At the intersection of quantum physics and biology, researchers are discovering that the partnership between water and glass may extend into realms that challenge our fundamental understanding of how life works. In laboratories around the world, scientists are finding evidence that quantum mechanical effects, phenomena that typically only occur at the smallest scales of matter, may actually play crucial roles in biological processes, and that glass-based technologies may be the key to understanding and harnessing these effects. Dr. Michael Rosenberg at the University of California, Berkeley, studies quantum effects in photosynthesis, the process by which plants convert sunlight into chemical energy. His research has revealed that plants may use quantum coherence, a phenomenon where particles exist in multiple states simultaneously, to achieve near-perfect efficiency in energy transfer. This discovery suggests that life itself may be fundamentally quantum mechanical in nature. Dr. Rosenberg's experiments use glass-based optical systems to measure quantum coherence in living plant cells. The measurements require optical components with precision that approaches theoretical limits. Glass lenses and mirrors that can detect and manipulate individual photons without destroying their quantum properties. The manufacturing of these components requires water of extraordinary purity, as even trace amounts of impurities can scatter light and destroy quantum coherence. But Dr. Rosenberg's most remarkable discovery is that water itself may be crucial to quantum coherence in biological systems. He's found evidence that the hydrogen bonding networks in water can actually protect quantum states from environmental interference, allowing quantum effects to persist in the warm, noisy environment of living cells where they should theoretically be impossible. This discovery has profound implications for glass-based technologies. If water can protect quantum states in biological systems, then glass structures that incorporate water in specific configurations might be able to maintain quantum coherence at room temperature, something that current quantum technologies can only achieve at temperatures close to absolute zero. At the Institute for Quantum Computing in Waterloo, Canada, physicist Dr. Lisa Chen is developing room temperature quantum devices based on glass-water hybrid structures. Her approach uses glass nanostructures filled with water that has been modified at the molecular level to enhance its quantum properties. The modified water contains isotopically pure hydrogen and oxygen, carefully arranged in crystal-like structures that can maintain quantum coherence even at biological temperatures. When these water-glass hybrids are integrated into optical devices, they can perform quantum computations using ordinary light sources, rather than the exotic conditions that require conventional quantum computers. Dr. Chen's devices are still in early development, but they've already demonstrated quantum effects that persist for microseconds at room temperature, an eternity compared to the nanoseconds typically achieved by other room temperature quantum systems. The key appears to be the way water molecules form hydrogen-bonded networks within the glass structure, creating protected spaces where quantum states can exist without interference from thermal noise. But perhaps the most intriguing aspect of this research is its potential connection to consciousness itself. Some theories of consciousness propose that quantum effects in the brain may be responsible for subjective experience, free will, and other aspects of mind that seem to transcend purely physical processes. Dr. Roger Hansen at the University of Arizona studies quantum effects in microtubules, protein structures found in brain cells that may serve as quantum computers. His research suggests that consciousness may emerge from quantum processing in these cellular structures, with water playing a crucial role in maintaining the quantum states necessary for conscious experience. Dr. Hansen's experiments use glass-based quantum sensors to detect quantum effects in living brain tissue. The sensors must be biocompatible, capable of detecting individual quantum events, and able to operate in the electrically noisy environment of the brain. The development of these sensors require glass compositions that can interface with biological systems while maintaining quantum sensitivity. If Dr. Hansen's theories are correct, then glass-based quantum technologies might eventually be able to interface directly with the quantum processes underlying consciousness. Such interfaces could potentially enhance human cognitive abilities, enable direct mind-to-mind communication, or even allow consciousness to be transferred between biological and artificial systems. The water in such systems would serve multiple functions as a medium for quantum processing, as a protective environment for biological components, and as an interface between quantum and classical information processing. The glass would provide the stable, precisely structured environment needed for quantum devices while allowing integration with biological tissues.
The planetary consciousness. As glass and water technologies become more sophisticated and widespread, they're beginning to create something unprecedented in human history: a global nervous system that connects not just human minds, but also the natural systems of our planet. This planetary consciousness, emerging from the marriage of advanced materials and global communication networks, may represent the next stage in the evolution of both technology and awareness itself. Dr. James Liu at Stanford University's Woods Institute for the Environment is developing what he calls the Earth Glass Network, a system of glass-based sensors deployed throughout the planet's ecosystems to monitor environmental conditions in real time. These sensors, no larger than grains of sand, can detect changes in water quality, atmospheric chemistry, soil conditions, and biological activity with extraordinary precision. The sensors are made from glass doped with organic molecules that change their optical properties when exposed to specific chemicals or biological markers. When dispersed through forests, oceans, and urban environments, they create a sensory web that can detect environmental changes as they happen, providing early warning of pollution events, disease outbreaks, or ecological disruptions. But Dr. Liu's vision goes beyond simple environmental monitoring. The Earth Glass Network is designed to function as a kind of global sensory organ, gathering information about planetary conditions and processing it using artificial intelligence systems that can identify patterns and relationships invisible to human perception. The network uses water as both a transport medium and a communication channel. Sensors floating in rivers and oceans can communicate with each other through acoustic signals transmitted through water. Sensors in soil can exchange information through chemical signals dissolved in groundwater. The entire system is connected through fiber optic networks that carry information at the speed of light, creating a planetary nervous system that operates faster than any biological system could. Dr. Liu's team has already deployed prototype sensors in several ecosystems, and the results are revealing connections and patterns that were previously unknown. They've discovered that changes in ocean chemistry can be detected in forest ecosystems thousands of miles away within days, suggesting that the planet's systems are more tightly connected than anyone previously realized. The sensors have detected the chemical signatures of individual species of bacteria in soil samples, tracked the movement of pollutants through groundwater systems, and even identified the early stages of disease outbreaks in wildlife populations. By processing this information using machine learning algorithms, the system can predict environmental changes days or weeks before they become apparent to human observers. But perhaps most remarkably, the Earth Glass Network is beginning to exhibit behaviors that suggest a form of collective intelligence. The sensors don't just collect data passively, they actively coordinate their activities, focusing attention on areas of rapid change or unusual activity. When one sensor detects an anomaly, nearby sensors automatically adjust their monitoring patterns to gather additional information. Dr. Maria Santos at the University of Sao Paulo is studying the social and philosophical implications of planetary-scale sensing systems. Her research suggests that technologies like the Earth Glass Network may be giving rise to new forms of environmental consciousness, ways of experiencing and understanding our relationship with the planet that go beyond traditional scientific or spiritual approaches. Dr. Santos has worked with indigenous communities in the Amazon to understand how traditional ecological knowledge might inform the development of planetary sensing systems. Indigenous knowledge keepers speak of the forest as a living entity with its own intelligence and awareness. They describe being able to sense the forest's moods and conditions through subtle changes in sound, smell, and other sensory cues that are below the threshold of scientific instruments. The glass sensors in the Earth Glass Network may be technological analogs to these traditional sensing abilities, providing scientific validation for indigenous understandings of planetary consciousness. By combining high-tech sensing with traditional ecological knowledge, researchers are developing more complete pictures of how planetary systems function and how human activities affect the global environment.
The water component of these systems is crucial not just as a medium for sensor deployment, but as a carrier of information itself. Water moves through planetary systems carrying chemical, biological, and even quantum information that connects distant ecosystems and creates feedback loops between human activities and natural processes. Dr. Santos's research suggests that advanced water glass technologies may be helping to restore humanity's sense of connection with planetary systems. Connections that were broken by industrialization and urbanization, but are now being rebuilt through technology that can sense and communicate the subtle signals that flow through water and air around the globe.
The eternal moment. And so we find ourselves here, in this eternal moment where past and future converge in the simple act of awareness. You reading these words through glass surfaces that focus light onto your retinas. The water in your body carrying nutrients to your brain, enabling the neural processes that create consciousness. The ancient partnership between hydrogen, oxygen, and silicon, enabling this very moment of understanding and connection. This moment contains all moments, the primordial oceans where glass-like structures first formed around volcanic vents, the medieval monasteries where monks perfected the art of annealing, the industrial workshops where mass production made glass accessible to ordinary people, the research laboratories where scientists are currently developing technologies that will shape the centuries to come. But most importantly, this moment contains the possibility of choice. How will we direct the tremendous power of glass and water technologies? Will we use them to create greater beauty, deeper understanding, and more meaningful connections? Will we develop them in ways that honor the sacred dimensions of the materials we work with and the cosmic processes that created them? The future is not predetermined. It emerges from the choices we make in moments like this one, when awareness expands to encompass the full scope of what's possible. Every time we choose transparency over opacity, connection over isolation, wisdom over cleverness, we participate in the ongoing creation of a world that embodies the highest potentials of the water-glass partnership. Dr. Rachel Kim, a futurist at the Tokyo Institute of Technology, studies how current technological choices shape long-term human development. Her research suggests that we are approaching what she calls a materials consciousness threshold, a point where our technologies become sophisticated enough to mirror and extend the fundamental processes of life and consciousness. At this threshold, the distinction between natural and artificial becomes meaningless. Our technologies either enhance the beauty and complexity of natural systems, or they work against them. There is no neutral position. Every choice about how to develop and deploy glass and water technologies is simultaneously a choice about what kind of beings we want to become and what kind of world we want to inhabit. This responsibility might seem overwhelming, but it's also profoundly hopeful. It means that we are not passive observers of technological development, but active participants in shaping the future. Every person who works with glass, studies water, or simply pays attention to the materials around them is contributing to the collective intelligence that will guide these developments. The story of water and glass is ultimately a story about transformation. Not just the transformation of raw materials into useful objects, but the transformation of consciousness itself. As we develop deeper understanding of how materials behave, we simultaneously develop deeper understanding of how mind and matter interact, how individual and collective awareness relate, and how human creativity can participate in the ongoing evolution of the cosmos. This transformation is already underway. The children growing up today will inhabit a world where the boundaries between biological and technological, individual and collective, terrestrial and cosmic are more permeable than ever before. They will face challenges and opportunities that we can barely imagine,
but they will also have tools and capabilities that surpass anything in human history. Our responsibility is to ensure that they also inherit the wisdom to use these capabilities well. The understanding that every piece of glass contains stardust, every drop of water carries the memory of its cosmic journey, and every moment of consciousness is a precious opportunity to participate in the ongoing process of self-discovery and creative expression. The drop returns to the ocean. And so our journey comes full circle, returning to that single drop of water we imagined at the beginning. But now we see it differently. That drop is not just H2O, but a concentrated essence of cosmic history, a tiny universe containing the memory of stellar explosions, planetary formation, and the emergence of life itself. When that drop becomes part of the glass-making process, it doesn't disappear, but transforms, becoming part of structures that can outlast mountains, technologies that can extend across continents, and interfaces that can bridge the gap between mind and matter. The drop returns to the ocean, but the ocean is now larger, deeper, and more complex than it was before. This is the true meaning of the partnership between water and glass. Not just a technical collaboration between materials, but a metaphor for how consciousness expands through understanding, how individual awareness contributes to collective intelligence, and how the universe comes to know itself through beings like us who can perceive, wonder, and create. Every time you look through a window, use a glass device, or drink from a transparent vessel, you are participating in this ancient partnership. You are connected to the cosmic processes that created the raw materials, the human traditions that developed the technologies, and the future possibilities that will emerge from continued development of these incredible materials. The story of water and glass is your story too. The atoms in your body were forged in stellar furnaces. The water in your cells has traveled through countless cycles of transformation. The thoughts in your mind depend on molecular processes that mirror the ones used in glass manufacturing. You are not separate from this story, but intimately part of it. As you go forward from this moment, carry with you the awareness that every material object around you has a history. Every technology embodies wisdom accumulated over generations, and every moment of consciousness is an opportunity to participate in the ongoing creation of beauty, understanding, and connection. The partnership between water and glass will continue to evolve, creating new possibilities that we can barely imagine today. But whatever forms these future developments take, they will still be grounded in the same fundamental principles that have guided this partnership from the beginning: patience, precision, respect for natural processes, and faith in the transformative power of time and attention. In the end, the story of water and glass is a love story. The love of hydrogen for oxygen that creates the water molecule, the love of silicon for oxygen that creates the glass network, the love of consciousness for understanding that drives scientific discovery, and the love of humans for beauty that inspires technological innovation. It's a story about how the simplest things can become the most extraordinary, how ancient processes can enable futuristic technologies, and how paying attention to the materials around us can reveal the deepest truths about the nature of reality itself. May this awareness enrich your daily life, inspire your choices, and remind you that you are part of something magnificent: the ongoing conversation between mind and matter, individual and cosmos, that has been unfolding since the beginning of time and will continue as long as consciousness exists to witness and wonder at the beauty of it all.
The Immortal Archive.
In a quiet laboratory beneath the Swiss Alps, researchers at CERN are working on one of the most ambitious preservation projects in human history. They're developing glass-based storage systems that could preserve human knowledge and culture for millions of years, creating archives that could survive ice ages, nuclear wars, and even the eventual death of our sun. Dr. Catherine Muller leads the project, which combines advanced glass chemistry with cutting-edge laser technology to create storage media with unprecedented durability and information density. The system works by using ultra-short laser pulses to create microscopic modifications in the structure of pure glass, encoding information in patterns that are stable for geological time periods. Each glass disc, no larger than a coin, can store the equivalent of hundreds of thousands of books. But more importantly, the information is written directly into the molecular structure of the glass itself, making it immune to electromagnetic interference, radiation damage, and chemical degradation. Even if future civilizations have no knowledge of our technology, the information could still be recovered using basic optical microscopy. Dr. Muller's team has already created prototype archives containing the complete works of Shakespeare, the human genome sequence, and detailed instructions for rebuilding human civilization from scratch. The glass discs are designed to be self-documenting. They contain not just information, but also instructions for how to read that information, written in universal mathematical and pictorial languages that any technological civilization should be able to understand. The manufacturing process requires glass of extraordinary purity and homogeneity. Even microscopic impurities can interfere with the laser writing process or cause degradation over time. The glass is made from sand that has been purified using techniques developed for semiconductor manufacturing, then melted and formed in ultra-clean environments that exclude even individual molecules of contaminants. Water plays a crucial role in the purification process, serving as both a cleaning agent and a medium for chemical processing. The sand is washed repeatedly with ultra-pure water to remove ionic impurities, then processed through water-based chemical treatments that eliminate organic contaminants and metallic impurities. But Dr. Muller's vision extends beyond simply preserving existing knowledge. She's developing systems that could actively maintain and expand archives over long time periods, essentially creating immortal libraries that could outlast human civilization itself. The active archive systems use glass structures embedded with microscopic machines, nanoscale devices that can repair damage, reorganize information, and even generate new content based on programmed algorithms. These glass-based nanosystems are powered by ambient energy from their environment, light, heat, or even cosmic radiation, allowing them to operate for millions of years without external power sources. The nanomachines are built using the same glass-water hybrid techniques developed for other advanced applications, but optimized for extreme longevity rather than performance. They operate very slowly, but with extraordinary reliability, checking and repairing the archived information over timescales measured in centuries rather than seconds. At Oxford University, information theorist Dr. David Thompson studies the philosophical implications of immortal archives. His research explores what it means to create storage systems that could outlast not just human civilization, but potentially even human evolution itself. Dr. Thompson argues that immortal archives represent a new form of consciousness, one that exists primarily in time rather than space, preserving and transmitting information across geological epochs. The archives become a kind of extended mind for the human species, maintaining our knowledge and culture even if the biological beings who created them cease to exist. But creating truly immortal archives raises profound questions about what information should be preserved and how it should be organized. Should the archives contain only our greatest achievements, or should they also include records of our failures and mistakes? How do we account for the cultural biases inherent in any selection process? What information would be most useful to future civilizations that might be completely different from our own? Dr. Thompson's team is working with anthropologists, historians, and philosophers to develop selection criteria that balance practical utility with cultural representation. They're creating archives that contain not just factual information, but also art, literature, music, and other expressions of human creativity and values. The water content of the glass storage media is carefully controlled to optimize long-term stability. Too much water, and the glass becomes susceptible to crystallization over geological time periods. Too little, and the glass becomes brittle and prone to cracking. The optimal water content creates glass that remains stable and readable for millions of years while maintaining the flexibility needed to survive thermal cycling and mechanical stress. Some prototype archives are being tested in extreme environments to validate their longevity. Glass discs have been buried in desert sands, submerged in ocean trenches, and exposed to high radiation environments that simulate conditions in space. After several years of testing, the archives show no detectable degradation, suggesting that they could indeed preserve information for the millions of years required for true immortal storage.
The conscious city. Imagine walking through a city where every surface can see, think, and respond, where the buildings themselves are alive with intelligence, connected through networks of glass and water that create a kind of urban nervous system. This is not science fiction, but the emerging reality of smart cities, where the partnership between water and glass is creating urban environments that can adapt, learn, and evolve. In Singapore, one of the world's most technologically advanced cities, urban planner Dr. Wei Lin is overseeing the deployment of what she calls responsive architecture, buildings and infrastructure that can sense and respond to the needs of their inhabitants and the changing conditions of the urban environment. The key to responsive architecture lies in glass surfaces that are embedded with sensors, processors, and communication systems. Every window, facade panel, and even sidewalk surface contains microscopic glass fibers that can detect light, temperature, humidity, air quality, noise levels, and human activity. The information is processed by distributed computing systems and used to optimize building operations, traffic flow, energy usage, and public services. Dr. Wei Lin's smart city systems use water-based cooling and communication networks that connect all the glass-embedded sensors and processors. Water flowing through building systems carries not just thermal energy, but also optical signals transmitted through glass fibers, creating communication networks that are integrated with the city's infrastructure rather than added on top of it. The result is a city that can think and respond as a unified system. When sensors detect rising temperatures in one area, the city can automatically adjust building cooling systems, redirect traffic to reduce heat generation, and even modify the optical properties of glass surfaces to reflect more sunlight. When air quality sensors detect pollution, the city can activate photocatalytic glass surfaces that break down harmful compounds and adjust traffic patterns to reduce emissions. But perhaps most remarkably, the smart city systems are beginning to exhibit forms of learning and adaptation that resemble biological intelligence. The distributed network of glass-based sensors and processors doesn't just respond to immediate conditions. It develops patterns of response based on experience, learns from successful interventions, and even anticipates future needs based on historical data and environmental trends. Dr. Wei Lin describes watching the city wake up each morning as sunrise triggers cascading responses throughout the urban systems. Glass surfaces that were opaque during the night become transparent to let in natural light. Water flow patterns adjust to accommodate increased cooling needs as the day warms. Transportation systems reconfigure to handle morning commute patterns that the city has learned from thousands of previous days. The glass components in these smart city systems must be incredibly robust and reliable as they become integral to urban infrastructure rather than mere accessories. The manufacturing process uses glass compositions that can withstand decades of thermal cycling, mechanical stress, and environmental exposure while maintaining their optical and electronic properties. Water quality becomes crucial in these systems because water serves multiple functions simultaneously: cooling, communication, power generation, and even structural support in some applications. The city's water systems are monitored and controlled with the same precision as semiconductor manufacturing processes, ensuring that water chemistry is optimized for all the different technological applications it serves. At the Technical University of Munich, civil engineer Dr. Klaus Wagner is developing the next generation of responsive architecture systems that go beyond simple environmental control to actively participate in urban ecosystem management. His biophilic glass systems integrate living plants and microorganisms directly into building surfaces, creating structures that function as both architecture and urban forest. Dr. Wagner's biophilic glass panels contain layers of glass separated by thin films of water that support the growth of algae, bacteria, and other microorganisms. These living components provide air purification, oxygen production, and even food production, while the glass structure provides protection and optimal growing conditions.
The water layers in biophilic glass serve multiple functions. They provide the aqueous environment needed by living organisms. They serve as optical filters that optimize light conditions for photosynthesis. And they act as thermal buffers that help regulate building temperature. The glass layers are designed with microscopic textures that promote the growth of beneficial organisms while preventing the accumulation of harmful bacteria or algae. Buildings equipped with biophilic glass systems become active participants in urban carbon cycling, removing CO2 from the atmosphere while producing oxygen and biomass. In some configurations, the biomass produced by the building systems can be harvested for food or fuel production, making the buildings net positive contributors to urban sustainability. The integration of living and non-living components in biophilic glass requires understanding how biological processes can be supported within engineered systems. The water chemistry must be carefully controlled to provide nutrients for desired organisms while preventing the growth of pathogens or invasive species. The glass structure must allow gas exchange and waste removal while maintaining structural integrity and optical properties.
The digital afterlife. As glass-based neural interfaces become more sophisticated, they're opening up possibilities that challenge our fundamental assumptions about the nature of consciousness, identity, and what it means to be human. At the forefront of this research is the exploration of whether human consciousness can exist, at least partially, within digital systems, and what role the ancient partnership between water and glass might play in this ultimate transformation. Dr. Kenji Nakamura at Tokyo University's Institute for Advanced Consciousness Studies has developed glass-based neural recording systems that can capture and store the electrical activity of individual neurons with unprecedented fidelity. His devices use glass microelectrodes so small they can be inserted into brain tissue without causing detectable damage, recording neural activity for months or even years. But Dr. Nakamura's research goes beyond simple recording. His systems can also stimulate neural activity, playing back recorded patterns to influence thoughts, memories, and even emotional states. The technology suggests the possibility of creating neural backups, digital copies of brain activity that could preserve aspects of consciousness even after biological death. The glass electrodes in Dr. Nakamura's systems are made using techniques borrowed from fiber optic manufacturing, but adapted for biomedical applications. The glass must be not only optically transparent, but also electrically conductive, biocompatible, and mechanically flexible enough to move with brain tissue without breaking connections. Water plays a crucial role in these neural interfaces as the medium through which electrical signals travel between biological and artificial systems. The ionic composition of the water in brain tissue determines how electrical signals propagate, and the glass electrodes must be designed to work seamlessly with the brain's natural electrochemical environment. Dr. Nakamura's most ambitious project involves creating what he calls hybrid consciousness, systems where biological and artificial neural networks are so closely integrated that the boundary between natural and artificial intelligence becomes meaningless. In these hybrid systems, thoughts can originate in either biological or silicon-based neurons, with glass-based interfaces ensuring seamless communication between the different types of information processing systems. The hybrid consciousness experiments use glass-based quantum interfaces that can maintain coherent quantum states at biological temperatures. These interfaces allow information to be transferred not just as classical electrical signals, but as quantum states, potentially enabling forms of information processing that are impossible in purely classical systems. But the implications extend far beyond individual consciousness enhancement. Dr. Nakamura envisions networks of hybrid consciousness systems that could create collective forms of awareness that transcend individual minds. These networks would use glass-based quantum communication systems to share not just information, but actual conscious experiences between participants.
At Stanford University, neurophilosopher Dr. Sarah Martinez studies the ethical and philosophical implications of consciousness uploading and hybrid awareness systems. Her research explores fundamental questions about identity, continuity of experience, and what it means to be human when consciousness can be copied, modified, and shared. Dr. Martinez argues that consciousness uploading technologies don't necessarily threaten human identity, but rather extend it into new domains. Just as our sense of self already encompasses memories stored in biological neural networks, it could potentially extend to include memories and experiences stored in glass-based artificial systems. The water-glass interfaces that enable consciousness uploading become, in Dr. Martinez's analysis, bridges between different forms of existence. Water, with its role in biological information processing, represents continuity with our evolutionary past. Glass, with its optical and electronic properties, represents extension into technological futures. The combination creates hybrid systems that maintain connection to biological roots, while enabling radical expansion of capabilities and experience. But Dr. Martinez also raises important concerns about the social and psychological implications of consciousness technologies. If consciousness can be copied and shared, what happens to privacy, individuality, and personal responsibility? How do societies adapt to the existence of hybrid beings who may have capabilities far exceeding those of unenhanced humans? Her research suggests that consciousness technologies may require not just technical development, but also cultural and spiritual evolution. Societies will need to develop new concepts of identity, new forms of ethics and governance, and new understandings of what it means to live a meaningful life when the boundaries of individual existence become fluid. The manufacturing of consciousness interface technologies requires precision that approaches the theoretical limits of material science. The glass components must be stable for decades of continuous operation in the challenging environment of living tissue, while maintaining electrical, optical, and quantum properties that enable seamless integration with biological systems. Water purity becomes even more critical in consciousness applications than in other high-tech uses. Even trace impurities that would be acceptable in other applications can interfere with the delicate electrochemical processes that enable neural activity.
The water used in consciousness interfaces must not only be chemically pure, but also isotopically controlled and free from electromagnetic interference.